So let's begin our review of the 2026 AP Chemistry FRQ solutions. These are the Mr. Grodsky solutions. This work, of course, is not endorsed by the College Board. I do not work for them. I don't represent them. And of course, my answers are only my personal interpretations of these problems. Nothing more, nothing less. The key that comes out later, or if you're watching this while the key comes out, again, this was made before the key, and this is what I think are the correct answers. The key might disagree. That comes out officially from me. Okay, with that all being said, let's be crazy and start in order with question 1. Question 1, the first question here, part A, I of a 10-point question. They're setting you up with a student performs a calorimetry experiment with KCl. That is basically the underlying theme of this question. But before we get there, they're asking you for the complete ground state configuration of the potassium ion. So I know some people would say, do I use shorthand? Can I use longhand? Well, very, very careful here, party people. If you look at, they want the potassium ion. Very easy to make this mistake. We see potassium here. I included the periodic table in the question here, and we can see our potassium here ends up on 4s1 right here. Now, because it loses an electron, it now has the same configuration as argon. So really there isn't an opportunity to write a shorthand if we're dealing with the configuration of that of argon. Of course, it's not argon. It achieves the same configuration. It loses one electron. If you look closely, potassium has 19 electrons, and now by losing one, hey, you lose a negative, you become positive. Now you're argon with 18. Now, of course, 18. Now, of course, we don't become argon. You're not losing a proton. You're losing electron, but you're becoming as stable as argon. Any case, we get the 1s2, 2s2, 2p6, 3s2, 3p6, right? Okay, so on to, and that should have been easy, 1I. Now 1II says which has the largest radius, the K plus or the K atom? This is part of the atomic structure part of the course. So you need to answer that question, and then you need to be very careful that you need to explain your reasoning using what? Principles of atomic structure. If you do not explain it with those principles, it will not be correct. So essentially, losing an electron, of course, that makes what we call the cation, means that you have one less electron. Now, you could answer this by saying that the remaining electrons feel the nucleus more, and I don't think that's the right way to explain that, nor does it explain using the principles of atomic structure. So if you say something along the lines that the remaining electron cloud has less electron repulsions, I don't believe you get the credit here. I think they were pointing to the fact we must use atomic structure. And when you think of atomic structure, we think of electrons filling in shells or principal energy levels, n numbers, or in sublevels or in orbitals. So when you talk about atomic structure, when it comes to electrons, and this is what this is about because the proton number is not changing because K is K, we're talking K stays as K, or potassium stays as potassium because the proton number stays constant. What we're talking about here is the arrangement of electrons. So by losing the 4s electron, now we have electrons that now occupy the third principal energy level. We were occupying the fourth. By losing that one valence, now you're occupying the third, and now you're getting closer to the answer. So that's what we needed to say. So the K atom is larger, or the K plus ion gets smaller, because the K plus ion has electrons now in the third shell. Okay, now what does that mean? Well, shells or principal energy levels, or n numbers, are indexed by size. As you increase the shell number, and you do so as you go down, okay, a group, you're filling electrons in shells that are subsequently farther and farther away from the nucleus. So this is about distance. Okay, so what we're saying here is that the K atom is larger than the K plus ion because the K plus ion lost its single valence electron in the fourth shell. Here I am talking about atomic structure, the structure of electrons. And the remaining outermost electrons are now occupying the third shell, which is closer to the nucleus. Really, this is all about distance, and all you needed to answer this question was that, hey, we've got electrons that are in a third shell now by removing an electron, and this shell is closer to the nucleus, which makes the ion smaller than the atom. Okay, so I'm moving on to the next question here. Question 1b here, we have a little blurb here that talks about a student performing an experiment to determine the enthalpy of solution, the energy change, the heat per mole of the dissolving compound of KCl. The student places water in a calorimeter, measures the initial temperature, adds KCl solid, and stirs until the KCl dissolves completely. The temperature is continuously monitored during the experiment. The data from the experiment is given below. They give you all this information you're going to need later on. But part B says describe how the student can use the temperature readings during the experiment to determine when the dissolution is complete. So don't get confused about dissolution. Dissolution is a word that describes, hey, the reaction or the process of dissolving KCl into its ions. In this case, we're measuring the energy change when that occurs. We call that dissolution, or delta H of the solution. Any case, so how do we know that the reaction is complete? Well, if you look very carefully, we have initial temperature of 24.5, and then we have a final temperature of 21.1. That's a negative 3.4 degrees Celsius change. Now, why would it decrease? Well, that must mean that energy is flowing into the reaction, right? So the solution is losing energy because the dissolving reaction, KCl breaking apart into K plus and Cl negative, is using that energy. Hey, it's endothermic. So how do I know this is over? How do I know that all of the KCl has dissolved? Well, the energy change will stop, meaning if the temperature is dropping, the reaction is going. When we run out of solid KCl to dissolve, you will run out of the energy that needs to be absorbed, in this case, to dissolve it. So the final temperature, or the decrease in temperature, okay, will halt, will stop. So you'll basically know when this is done when you find the coldest possible temperature, right? So I said that the solution, or the dissolving, is complete when the temperature of the solution does not decrease any further. Or you probably could say that just when the temperature starts to increase, or just when the temperature doesn't change anymore, right? It should continuously drop until all of the KCl dissolves. So when the temperature is decreasing and then it doesn't get past that temperature or just starts to warm up, you know that's the point where the solution is no longer absorbing energy, which means KCl is no longer dissolving. We've run out of it. It's the limiting reagent. On to 1C. Question 1C, here we are calculating the thermal energy, or Q, in joules. As they tell us, important that we understand that we have to answer in terms of what they ask for, transferred in this solution or dissolution reaction. Show the work that leads to your answer and assume that this solution has a specific heat capacity of 3.95. So on the previous page, they gave us a list of data. They gave us the final temperature. They gave us the initial temperature. So we have a change of negative 3.4. And they also just told us the specific heat is 3.95. And the tricky part here is that the mass of the water and the KCl must be added together to get to your mass of your solution. So the setup that people get wrong, or the setup they forget that usually leads to wrong answers, is the Q of your reaction, which is in this case the Q of the dissolution, that's the heat change, is equal to the negative Q of the solution, or the calorimeter, right? What we're doing is we're measuring the surrounding. Calorimetry is measuring the energy change of the surrounding. So the surrounding Q is what we're doing here. We're going to measure what happens to the surrounding. Now just think of the chemical reaction where we have something dissolving in different places, and then we have, you know, the container, and then of course very simply the energy change. In this case, we know the temperature is dropping, so energy is going into the dissolving, so the energy is dropping. So we're trying to get this total energy change that's occurring by the reaction or the reacting chemicals as they get hydrated with water. So we're after the Q of the dissolution, but we can't get it directly because it's changing, it's dissolving. So we can't do that. All we can do is get the surrounding temperature of the calorimeter, which we'll call the solution. And to do that, we need the mass of the solution, right? So the mass of the solution is the mass of the water plus the KCl. So on the previous page, if you add the water and the mass of the KCl, you'll get 103. That's the part that people tend to get wrong here. The mass of the solution. We're going to use a solution to figure out what's happening in the reaction in the solution. And you'll say, well, isn't it one the same? No, not really. The KQ, or the breaking up of the KCl, the decomposition, or I should say the dissociation, better word, of the K plus and Cl negative from its crystal lattice of the solid, is going to absorb energy here, and then it's going to give it to the remaining solution. So we've got to find the Q of the solution, which is MC change in T. As I said, the mass of the solution, the specific heat of the solution, and in this case, the change in temperature of the solution. They're always on the same team. Always use the same team, which is the solution. And of course, I get a negative 1400 joules here. And don't forget there's a negative in front here. And you say, why do we have that there? Again, it's the same energy. We're using the law of conservation of mass. The energy that is in this case, absorbed, I should say, in this reaction, because the temperature is dropping, that tells me that the surrounding calorimeter, the solution's losing the energy, and that the energy is going into the reaction. That tells me that I know that the Q of the solution, okay, is going to be negative, right? It's losing energy. The negative 3.4 times the specific heat times the what? The mass is going to give me a negative value for the Q of the solution. And then we have to times it by this negative, right? Because as I just said, the energy that is absorbed by the reaction is the same energy lost by the solution, but the difference, we put a negative here because they're going in a different direction, right? So this makes some sense here. So we get a negative value for the energy of the solution. Now timesing it by a negative gives me a positive 1400 joules. Now why is it positive? Because the what? Solution was absorbing the heat. It makes sense. So it's a good setup to keep track of the direction. You don't need the positive, right? You're solving for the magnitude, so we don't need the positive or the negative, but you will need it for the next question when you calculate the delta H. The delta H is a state function, and it's a change. This symbol here is a change, and we need to know if energy is going into the chemical reaction or out, and there is where we need a negative. Here, we're just solving for the magnitude. All right, so if that makes any sense, the 1400. And by the way, I'm using two sig figs here only because when I subtract the 21.1, 24.5 from the 21.1, I get 3.4, and that's the rule. You round off to the least number of decimal places, and now I have two sig figures, and it's the least number throughout. Please remember your units to remind yourself what they're asking for. They wanted joules here. Okay, so that is part CI. Let's go on to part CII, Captain. All right, sorry, that's going to be my joke continuously. So let's go through here, and we go to II. We can see that I'm going to take the Q of dissolution, which is going to be 1400 joules, and now I am going to convert it to kilojoules. Why? Because they asked me to calculate the value of the molar enthalpy of solution in kilojoules per mole. Well, I'm in joules, so I better put that in kilojoules. If I don't, this question is wrong. Okay, so now I got my 1 point, and by the way, we found from the previous question that because energy was being absorbed by the chemical, okay, the Q of the dissolution is a positive 1.4. Okay, it was a positive 1.4. Now I know I have a negative here. I need to fix that. Okay, that should be a positive. So the Q of the dissolution here, the Q of the solution or dissolution is equal to positive 1400, right? Because it was taking in, its energy is going up as energy was flowing to it. How do I know? The temperature dropped. And that's why we do Q in the previous question. You really should set yourself up with Q of the reaction equals negative Q of the surrounding water or solution or calorimeter. Any case. So now the next part is I need moles. Well, they're very nice to give us the moles of the KCl that was used. All right, and so that didn't need to be calculated. I'm just going to put that here because we know that's what kilojoules per mole. And then when I do the math, I get 15 kilojoules per mole, maintaining my 2 sig figs from the measurement unit. And this needs to be positive. It is endothermic, right? The surrounding temperature is decreasing. So on to part D. Number 1D, the question states the calorimeter is not perfectly insulated, which is a problem with all calorimetry experiments, although we assume the only energy transferring is between the reaction and its surroundings, or the surroundings and the reaction. The problem is that we do have energy that either leaks out or leaks in because calorimeters are not closed systems. So we know that this is a problem. So the second part of this question states, would this cause the magnitude of the energy per mole calculated that we just did in part C II to be greater than, less than, or equal to? Well, it would be less than. It normally is less than. In this case, because the calorimeter is not perfectly insulated and the temperature inside the calorimeter is dropping, that means that the heat is going to be able to flow from the cup and the surroundings into the colder solution. Now, if heat is flowing into, whether it be through the calorimeter, through the side or the top here, if we're contributing energy from the surroundings into a solution that's supposed to get colder, the temperature change will not drop as much as we expect or predict because we keep adding heat from the environment through the calorimeter, through the lack of it being insulated. So we got a value to be negative 3.4, if you remember in the earlier questions. Well, it's going to be a smaller temperature change. And the reasoning is because, well, if we're trying to drop the temperature because more and more KCl is absorbing heat, if heat is finding its way into the calorimeter from the surroundings, then that temperature change is going to be compromised. It's not going to be as low because we keep adding heat from the surroundings. Therefore, it doesn't get as low as we would expect. And if the temperature change isn't as great as what we expect, then guess what? Q is going to be smaller. So if you need to see this, very simple, Q is equal to MC change of T. Now the mass of the solution, the specific heat's the same, but our temperature change will be smaller. It won't be as low and as cold as we expect because heat's going to run in. So the temperature change is smaller, so your Q is going to be, the thermal energy is going to be smaller. And of course, how did you solve for delta H? You took the Q and divided it by the moles, right? So a smaller Q is going to lead to, of course, a smaller value of the enthalpy of the reaction. All right, so there it is. So on to part E. Part E. I know this question is probably going to get a lot of students, or did get you in terms of its difficulty, but it is a simplified problem if you break it down, I think, best with math. I did it both ways. I didn't say justify with a calculation, but certainly I think it's probably easier if you do that. So let's get after this. So in this question, a student performs a second experiment. So to set this up, there was already an experiment that was done where delta H was measured, and there was a temperature change in that reaction, or in that calorimeter, of negative 0.34. Now we're going to use this another experiment, same calorimetry, okay, but we're going to use rubidium chloride, okay, instead of potassium chloride that we used originally. All right, but we're going to use the same mass in grams. We're also going to have the same delta H of solution that results, okay? And of course, we're going to use the same specific heat. So everything's the same except we're dealing with rubidium chloride. So a couple of things you should recognize is that rubidium chloride has a different molecular mass than potassium chloride. And rubidium is much farther down the group. Okay, remember potassium is a group 1 ion and rubidium is farther down. Rubidium has an atomic mass of 85.47, okay, and of course potassium is around 41. So the point there is that, well, because rubidium is heavier, even though the formula is the same, there's going to be less moles. You have to recognize there's going to be less moles here, all right? Now, everything else is the same. So I tried to answer this. And again, the question says, is the magnitude of the temperature change with the second experiment using rubidium chloride greater than, less than, or equal to that of the KCl experiment? So we're basically after the temperature change. So I tried to answer this with an explanation using a formula, but not doing the calculation. And it's a little bit tough, I think, but here's how I went after it. I had to realize that the moles, now what I did here was I took the formula here to measure the delta H of the solution, which of course is going to be Q of the dissolution that we solve for divided by the moles. And so that's what I have here. Okay, let me try to explain how it changes. Because the Q of the solution is MC change in T, okay, from the previous questions, I just put those values there, except I left out the change in temperature. All right, now the moles that we use are going to be smaller. So in the previous question, okay, it was a smaller amount of moles. And this one I calculated for. I took these 6.8 grams of rubidium and I actually did the formula mass and I found that the moles were smaller. You didn't have to find that number if you're not trying to use a calculation, but I put there anyway because I'm going to use a calculation, I think, which winds up being easier to explain. So in any case, all I'm saying is with a lower amount of moles, and this number have to be the same, if you decrease your denominator, keeping the whole value of the equation the same, well then the top number's got to decrease, right? Because if you're going to decrease your denominator, that means, and keep this constant, okay, the only way to keep this constant is that the numerator's got to get smaller, because anytime you essentially increase a denominator, the value increases. So they said that the enthalpy, okay, is approximately equal. So keeping this the same, the only thing we can do to combat the decrease in moles, which should increase it, we have to decrease the numerator. Since the mass of the solution is not changing, because they're saying this, we're using the same mass that we used in the first experiment, and the specific heat, who has to decrease? Well, the temperature change does. Okay, and so you can put that to words. I said the magnitude of the delta T in the rubidium chloride experiment is less than that of the KCl if the moles of rubidium is less than, and the delta S in mass of solution and the specific heat are the same. I think it probably is easier if you just plug in. So if you take this same equation and you do your algebra and you solve for delta H, okay, with the values we have here, obviously we still had to have the number of moles of rubidium chloride, all right, and I converted my kilojoules into joules. Don't forget, party people, that the 3.95, which there should be a point there, the 3.95 is in what? Is in joules, okay, per gram per degree Celsius. All right, so I had to be in joules, so the joules cancel. All right, moles cancel and left with 1 over, okay, 1 over degrees Celsius, which gives me my temperature change. So when you solve for it, you get 2.1. And you compare that temperature change to the 3.4, you can see that it's less. So I think it's probably maybe easy just to go calculate it. But in any case, I know a lot of people kind of fumbled on that question a little bit, only because there was so much information. Slow yourself down and see what they're doing. I always tell my students there's always a what? An easy answer for every one of these questions. All right, so yeah, that's the way to look at that. So therefore the temperature decrease, the justification is that if you're going to have more moles of the compound, you're actually going to have less particles of rubidium chloride, okay, to absorb energy. That's really another way to say it as well if you don't want to use the mathematical equation. I tend to always look at the mathematical equation. It's finite. All right, so on to 1F. Number 1F, got a little blurb here. We have rubidium chloride, has a KSP of 57 at 20. I thought that was a typo at first, but then I realized rubidium chloride is pretty soluble. Don't normally deal with KSPs that are greater than 1, so this is another kind of curveball the test is throwing at many of these students. Okay, I thought the last question in 1E was a little bit, but in any case, let's continue on with part FI here. Write a net ion equation. Here, net ion equation, we're going to eliminate any spectators, but in this case, we're just talking about the dissolution, or the dissociation, I should say, of the rubidium chloride into its ions. You may say it didn't ask for the phases. I do believe you should always write the phases to distinguish between the salt that's a crystal and the ions that are in water that are dissolved. Okay, so that's pretty straightforward. The +1, -1 charges, we should know rubidium are based on the fact that rubidium's in the first column. It's an alkali metal. All of them have 1 valence electrons they like to lose, and the halogens like chlorine, fluorine, bromide, iodine need to gain 1 or like to gain 1, okay, over across the periodic table. So that should be straightforward. Okay, so on to number FII. So FII here states that calculate the molar solubility. When you hear the word molar solubility, I always scream at my students, we're solving for X, right? We're solving for how much this solid goes forward. And the key here is that they're saying the word saturated. Saturated means we're in a what? We're at equilibrium, saturated solutions. So when they want to solve for the molar solubility, they're looking for exactly this. They're looking for what is the concentration of the salt, okay, as a value of X, one of them, because for every one formula, there's one of the ions. If it's a 1-to-1, in this case, they both are, okay? So in any case, we're looking for the value of X, one of the values. They're going to be the same. So I don't think you need to have a equilibrium ice table to understand that this is going to be X squared equals 57 and then square root both sides right away. Now if this was a 2 here, if there was a coefficient of 2, which there's not, this would be 2 squared, that'd be 4x cubed that you'd be solving for. So we're kind of jumping the gun here, but that should be, obviously every one of these rubidium chlorides becomes one of these and one of these, so this becomes X and X. And because they said saturated, remember, what's in these brackets is molarity. That's what molar solubility is when the reaction, this reaction, is at equilibrium. So what are these concentrations? Well, they gave us the KSP. So basically, to solve for the exact concentration equilibrium, to solve for X, molar solubility, solve for X, all right, we're going to just take our KSP value and equal to X squared, and then square root both sides, and I get 7.6 molar is each X, and that's pretty high, especially if you're dealing with KSPs with very small values, because they're, you know, you're used to dealing with salts with KSPs that don't dissolve very well. That's the whole point of using them. So here we are using them for a very soluble salt, so I'd expect the molarity to be very high. So the answer, of course, is 7.6 molar. On to number 1FII. 1FII. So here we are with this question here. They said a second saturated solution. Again, saturated means we're in equilibrium. So I can use my KSP or my equilibrium expressions to answer some things for the amount of ions that solution is prepared by dissolving rubidium chloride in 1 molar KCl. Well, that's different. We're going to drop some rubidium chloride into solution that already has K pluses and Cl negative. We should know, okay, that KCl is going to dissociate into K plus and Cl negative ions. Now K plus is not in the overall reaction, right? Rubidium chloride is going to break apart into rubidium ions and chloride ions. So by having a 1 molar solution of KCl, what we have is we have the common ion effect. We already have chloride ions in there. So when we deposit some more rubidium ions, which are going to be +1, we're going to have a large amount of chloride ions. So there's a common ion that this solution already has to the reaction of rubidium trying to dissociate. That's what we have here. So this is trying to dissociate normally and then reach equilibrium, okay, because we're saying we're preparing a second saturated solution, yet we're doing it where there's already chloride ions available because of the KCl. The K plus isn't in the solution, so it spectates. So this is a common ion effect. So here comes the question, okay, will this molar solubility, and again, people get lost in the sauce here, the molar solubility is the what? Is the X, right? Now, so it's the how much this salt goes forward. Will the molar solubility in a 1 molar KCl solution be greater, less than, or equal to the molar solubility calculated in part FII above? Now, we calculated 7.6. All right, well, here's the deal. You could definitely justify this because you need to answer the question and justify it either mathematically or with words. And I think either one is easy here. Probably the math is a little more difficult if you don't see a little catch here. But let's go with the words. Here's what I know. Because of the common ion that's already there, because we have a large amount of chloride ions, and we're at equilibrium, that's important, we can use the Le Chatelier's principle to justify. So we can say that by having a common ion of chloride ions, as we try to dissolve the rubidium chloride, because of the larger than usual amount of chloride ions, we're going to stress the reaction at equilibrium, and the reaction is going to shift in a way to lower the solubility of rubidium chloride. Bottom line is you basically, through the common ion effect, have a greater amount of chloride ions, which means the reaction is going to shift to the reverse reaction to use up the chloride ions. As it lowers the chloride ions, because that's what Le Chatelier's principle does, it relieves the stress by working back toward the equilibrium. So to shift to the left, to the Beyonce, that means the chloride ions have to get used up. That's the whole purpose, but you're going to use up some rubidium. So there would be a decrease, all right? So the molar solubility will be less, okay? There'll be less of the rubidium +1, but there's less of this going forward because the reverse reaction is initially going to be more spontaneous due to Le Chatelier's principle. Okay, so I said the molar solubility will be less for rubidium if the rubidium chloride is dissolved in a 1 molar solution. So just using some common language that you have in the course, because of the common ion, the reaction would shift to decrease the solubility due to adding a common ion due to Le Chatelier's principle. All right. Now, I love the math that you can do. I know that KSP is equal to this formula. It's a 1-to-1. And I know the KSP from the previous problem is 57. Now, I'm going to solve for the rubidium, the X here, knowing full well that this number is going to be elevated. Now, how is it elevated? Well, we found out that it should be 7.6 molar. That's what we just calculated in this question here. Now, you don't have to calculate, but I'm going to explain it. So because we have a 1 molar, that would mean that this value is now 8.6. What's that going to do to the X? Well, it's got to decrease it. If this number comes up, this number is going to come down. If what? If we have to keep this number the same, right? So this is going up, this has to come down, and you could solve for it. So again, the 8.6 is the 7.6. I'm adding the 1 molar amount of chloride ions to that, and then I'm solving for X, and I get 6.6, which is clearly less than 7.6. That could be my justification. So I could have clearly just said less and then did this calculation. All right, so in any case, on to question number 2. Question 2, part A. This is version J in our part of the world here. So in this question 2, the overall theme of the question is, and all the parts below it are about the chromate and dichromate ion. In part A, they want you to predict the molecular geometry. Of course, that's the geometry of where the atoms are surrounding the central atom. Now, I say that because you have to be aware that if the central atom has lone pairs, that would affect the geometry in trying to predict it. Remember, the lone pairs and the bonding electrons in the central atom repel themselves into the most stable shape to minimize repulsions. These have electrons density. So the electron density that exists either in a lone pair for the central atom or bonding pairs will determine how they repel themselves to minimize repulsions and gain a stable lowest energy shape. If you ever did or saw the demonstration where the teacher blows up balloons and ties them together, it's a great example how the balloons will push themselves actually into these shapes. But careful, molecular geometry is a little different than electron domain geometry. Now in this case, it's the same because chromium doesn't have any lone pairs. I must mention that because if I'm trying to teach you about this problem, I want you to understand about other problems that are related. Now get back to this question. We take a look at the chromate ion here. The thing I want you to recognize is how many electron domains does it have? This is how we figure out how this atom, or in this case this ion I should say, repels itself. You notice they said based on VSEPR theory, and some people might be turned off or like confused about that. That's the valence shell electron pair repulsion theory, and that just means how these balloons or these negative electrons, whether in a lone pair or in a bond, repel themselves to minimize repulsions and gain that stable structure. So that's all we're talking about here. So let's get after this and find how many actual regions of electrons we have. Now we don't have any lone pairs. We would count that for the central atom. Remember, it's the central atom that determines the shape. So if I count 1, 2, 3, and then 4, okay, that would be the 4 different domains, 4 different regions of electron density that will repel themselves. When I say that, these electrons here are going to repel these electrons here, right? So they're going to repel and push off, and the same thing here. So what shape do they take? Now on paper it looks like it's a shape of a T, but that is a 2-dimensional drawing when these things exist in 3 dimensions. So again, count the domains. We have 4. And with 4 domains, we have a molecular geometry of a tetrahedral. It's important to understand molecular geometry. Now, we also have the electron domain geometry as a tetrahedral, right? Another way to think about this, too, is that there is 4 domains only, and that would mean that this is an sp3 hybridized orbitals that surround. You say, well, why am I going into hybridization? They're not asking that. Well, this is tied together. And why do I know it's sp3 and why am I bringing it up? Because to me, it's a great way to tie in other concepts that are totally related. So if you look at sp3, that means an s orbital, which is a circular orbital, and then 3 p orbitals. You should know there's 3 of them. Each holds 2, right? There's a total of 4 orbitals that mix together. The p orbital is a dumbbell shape. You don't have to know that, but if they mix together, they're going to make 4 evenly separated, or I should say, they're going to make 4 hybrid orbitals that are called sp3 orbitals that are the same size and same electron density. That's important because these orbitals here have to have the same. Now these orbitals are overlapping here, but this is like if I'm just drawing the orbital that's extending out. They have to have the same electron density, okay, as the other 3 so that they repel themselves evenly. If one had more electron density than the other, then they would push off and not create an even bond angle, which you should know for tetrahedrals is 109.5. So that's very important. So reason why I'm going to the sp3 is that when you're in the sp3 family, that's when you have 4 regions of electrons. That means your electron domain geometry, where electrons are, is tetrahedral. Then you could have the tetrahedral shape. Now there are other molecular shapes in this family. Just to point out a couple of them, let's look at ammonia, which is NH3. It has 5 valence electrons, so it's going to make this shape here. And if we count domains, we can see that there is 1, 2, 3, and 4. Notice I counted the lone pair. Okay, so this would have electron domain geometry that where the electrons would repel themselves, including the lone pair, into a tetrahedral shape. So if they asked for electron domain geometry, this would be tetrahedral. But if you ask me what the molecular geometry, where the atoms are, this would not be a tetrahedral. Okay, certainly the electrons would point outward or into a tetrahedral shape, a side of 4 tetrahedral, but where the atoms are, this would be the molecular geometry would be a trigonal pyramidal shape, top of a 3-sided pyramid. Another great example in the sp3 family, I say family, it's the way I do it, is water. So you have water, and you say, well, water's bending downward. Well, why? There's 2 lone pairs here. And these 2 lone pairs are going to repel downward the bonds between, or electron density, which is the bonds between the oxygen and the hydrogen. Now, why would they bend them downward? Well, because electrons repel themselves. So again, if we count electron domains, I'll do here with the pencil, you get 1, 2, 3, 4. You bet. Okay, that electron domain geometry is a tetrahedral. But where the atoms are, we call this bent. So in the sp3 family, where there's 4 equal hybrid orbitals that are mixed together by s and 3 p's of the same electron density, they're going to repel themselves evenly into a tetrahedral for the electrons. If you have 4 atoms in those 4 positions, then the molecular geometry is a tetrahedral. If you have 3, it's trigonal pyramidal, and if you have 2, it's bent. You need to know the distinction here. Now, they were just asking for the molecular geometry, therefore this is a tetrahedral. Electron domain geometry is also a tetrahedral. All right, so on to question 2II. Question 2AII. On figure 2, draw a complete Lewis diagram for a resonance structure of the chromite ion that results in a formal charge of 0 on 2 of the atoms and a formal charge of -1 on the other 2 atoms. Your diagram should contain the same number of valence electrons. So what they mean by the same number of valence electrons is this drawing that they gave you is suggesting that it already has all the electrons it needs to become the -2 charge. It gained 2 from the environment. And what they're just saying is you're not going to add any more electrons to make this occur. So you should recognize that there are 2 electrons, right, for every dash. Okay, that being said, all I'm really going to do, or we're going to do here, is move electrons from the oxygens into this position of chromate. Now, you know, chromium, the essential atom, is beyond row 2, so it could have more than an octet. That's something you should recognize first, all right, because it does have the d electrons. But in order to know how to put the number of electrons or move the electrons to satisfy a formal charge of 0, we have to know what formal charge is. So formal charge is a way of bookkeeping where the electrons we draw in a Lewis dot diagram and where they have been moved to and where they came from. So in this case, formal charge, and I wrote it right here, formal charge is equal to the valence electrons, those electrons they start with, those are the outermost, minus the assigned electrons, which are, hey, they're lone electrons, that could be a pair, plus half the bonding because, well, they're sharing electrons in a covalent bond, so half of their electrons are going to be shared. So in order to get a formal charge of 0 on an oxygen atom, I had to draw a double bond. So what I did here, and let's get a little closer here, what I did is I took a pair of electrons. Remember, there was 3 pairs, right? So when you have a single bond, because I didn't change these oxygens here, right? So they had 3 pairs. So to create a double bond, all I did was move, okay, a pair there. Now, of course, I didn't change that one. So where I have a double bond, which, let's say this pair here was originally back here. Okay, so I basically moved a pair of electrons there. Now, why did I do that? Well, I wanted a formal charge of 0 like the question stated. So I took my valence electrons, which is 6, we should know that, and then we minus the 6 assigned electrons. Now, what are the 6 assigned electrons? Well, the 6 assigned electrons are all of its lone pairs plus half its bonding. I love to draw circles when I'm doing formal charges, right? So those are the electrons this oxygen is owning for this structure, okay? And it's owning 6, and it showed up with 6. So therefore, it's using everything it showed up with, therefore the formal charge is 0. And for the same reasoning, this one needed a double bond to do the same thing. So a formal charge is 0. The question was just telling you, put a double bond there. Oxygens love double bonds. Why? Well, they want to go from a 6 valence electron to have the octet rule. They are a what? They are a row 2 element that follows the octet rule. So that's important. So that's what they really were saying there. Now, how about this -1 on the other oxygens that we're not going to change? Well, do the same thing. I'm going to put a circle. It owns what electrons? Well, it's starting with 6, but in this case, it has 7 assigned. That means that's how much it's using in this diagram. So we're going to circle this 6, and then, of course, remember, that's all the lone pairs are finally assigned, and then what? Half its bonding. So half its bonding right there means it has 7. It's utilizing 7 in this diagram, and guess what? It starts out with 6. So somehow it's gaining 1 to exist as a single bonded oxygen, and that's why it has the formal charge of -1. All right, and if you wanted to do chromium, by the way, this oxygen here would be here. So if you want to do the Lewis, again, the formal charge for chromium, you can see the remaining electrons are what the chromium is owning in this structure. So that's how we do formal charges. Now, just a little review of formal charges. Oxygen is more stable in the formal charge state of 0, right? That's where it's the most stable, right? That's where it's actually kind of filling its octet. All right, so that's important. Now, what I did is I also put another way you could have drawn that, and that's to the right here, by putting the double bonds here. Now, of course, I could have had the double bonds in the other position, or as long as I had 2 double bonds. And make sure when you draw 2 double bonds, you have the right number of lone pairs, because we're utilizing a pair to make this bond, as you can see by my color coding. So we should have 2 lone pairs for the double bond. I don't care where you put them, it wouldn't matter. It could be alternating if you want to be fancy, and then you need 2 single bonds. And of course, if you have a single bond, you better have your 3 lone pairs. So this would be an equally correct structure here. All right, so on to the next question. So part BI, write a balanced net ionic equation. That's important, net. That means we're going to take out any spectators, the overall change equation for the reaction between the chromate ion and a strong acid. And they're telling you it's a strong acid in a couple different places. Okay, so if your teacher said you must know your strong acids, well, that's true, because there's been so many questions in review questions where you needed to know that. So any case, we've got ourselves a strong acid. Now, something about strong acids that we should recognize is that they completely dissociate. So if I was to write this reaction here, NO3 is going to completely dissociate into a proton, and of course the nitrate ion, NO3 -1. Okay, so that is going to completely dissociate. So anytime we're writing a net ion equation, we never write the combined compound of a strong electrolyte. Electrolytes are things that completely dissociate into ions. That would be soluble salts, or in this case, acids or bases that completely dissociate. So anything that completely separates, we always separate it. So in truth, this reaction has an H plus a nitrate. Now, the nitrate's not part of the reaction, because they're telling me that we're dealing with the nitric acid, strong acid, and the dichromate, and then we're producing the chromate ion, I'm sorry, so the nitric acid and the chromate ion, and then we're going to produce the dichromate ion and water. So you see, nitrate or no N's are a part of this reaction. You don't see any nitrogens anywhere in the product side, so that nitrate would be on both sides of the reaction, which means if I'm going to use one nitrate, or in this case 2, as when we will balance, and I produce 2 nitrates, I'm not using them, this would cancel. So we don't ever add spectators. Okay, they're not part of the overall reaction, so let's kind of get rid of them. And understand that we're going to start with a proton. Now I have of course the reaction written here. So I'm going to start with a proton, and then I'm writing the chromate ion, and then I'm writing the dichromate and water. So how did I come up with 2 to 2 to balance this reaction? Okay, this net ion reaction. Well, the first thing I do is I see that my product, and again, this is a puzzle, many ways to skin a cat. I go navel up. I love cats, but you got to skin them right. In any case, I have 2 chromate ions, right? There's a 2 here. I only have 1. So I was forced to put at least a 2 here. Now, of course, these things can change. This is a puzzle. Now, what that does is gives me 2 times 4. That's 8 oxygens. And I already see that I have 7 with 1 chromate, and I already see that I have 1 from 1 water, so that would give me the 8. That's good. Notice something, I have 2 hydrogens here, and if I started out with a proton, I would need to write a 2 here. And that's where I came up with the 2, 2. And of course, nothing in front implies a 1. All right, so again, that's the balanced reaction overall. On to number BII. Number 2, BII. Is the reaction a redox reaction? I have the reaction that we just balanced in 2BI, and they want to know if it's a redox reaction. They say justify your answer based on the oxidation number of chromium. Just as a word of caution, anytime the AP is asking for whether a reaction is redox, you should always answer with oxidation numbers and see if they're changing. If oxidation numbers are changing, electrons are being lost and gained, that means it's redox. Reduction is gaining, oxidation is losing, so let's go right after it. So they want to see if the chromium in the reactant, okay, is going to have the same oxidation as the chromium in the product. So I kind of condensed this right here. So let's take a little look here. And this is how I do oxidation numbers. I know that the charge of the ion is -2. So I make the bottom numbers equal to that. Now, if it wasn't an ion, it would equal 0. Now, I know that oxygen is -2 because on the periodic table, it needs 2 electrons to fill its octet. So it likes to become -2. And there's 4 of them. So 2 times 4 is my -8. What number plus a -8 is -2? You guessed it, +6. Since there's 1 chromium, the individual oxidation state is +6. How do I do it over here? Same idea. The whole charge of the chemical species is -2. So I write that here. Same thing. Oxygen is -2 individually. The top numbers are the individual charges, by the way, that we care about. I use the overall charges on the bottom to get the individual charges on top if I didn't say that in the first one. In any case, I have the individual charge of oxygen to be -2. There's 7 of them. So 2 times -2 times 7 is -14. I'm going to add that to some number that I have to figure out to give me a -2. So a -14 plus what number is -2, I solve for that to be +12. And because there's 2 of them, each chromium must be +6. So what do we find through this exercise of getting oxidation numbers? That the chromium oxidation state from reactants to products do not change. Okay, neither does any other atom, so therefore this is not a redox reaction. All right, so that's as easy as it is assigning oxidation numbers and seeing if they change. They were pointing to you to the chromium. So on to the next question. Number 2C. Is the reaction represented by equation 2 thermodynamically favorable? I hear that. I think delta G is negative or unfavorable under standard conditions. Justify your answer with a calculation of delta G. Well, since they gave me a voltage or a net potential here, I'm going to use the formula of delta G minus, don't forget that, N FE0 of cell. All right, that's the one we're going to use here. And we're going to plug this value in. Notice it's negative, it's non-spontaneous. Volts which is going to lead to a positive delta G. Any case, you plug the value in, and then of course you're going to use Faraday's constant that's given to you in your reference table. I wrote that right there for you. And then this N means moles of electrons in the balanced equation. In this case, we're dealing with this half reaction only, so we put 6 here. And of course, we do the math, and we get positive, because a negative times a negative is a positive value. So right away, delta G is 0. But we get, of course, 764,000 joules. All right. And I did round to 3 sig figs because I started with 3 here, and it was the least significant number. I don't believe this 6 electrons would count here, but I did round to 3. Any case, not absolutely necessary there, but the whole point here is that justify your answer. Is this thermodynamically favorable? Hey, it's got a positive value. Don't forget, this negative times a negative gives me positive value for delta G, which means free energy is going into a reaction. And when free energy is going into a reaction, we're giving it the energy to make it happen. Remember, spontaneous reactions that are thermodynamically favorable, they occur without an input of free energy. They give off the free energy to drive and couple other reactions. In any case, the equation, the value is positive, therefore it's thermodynamically unfavorable due to a delta G that's positive. All right, so that's what they wanted the calculation for, and that's basically it. So on to part D. Number 2, part D. I know a lot of students struggle with this question. Okay, these types of questions dealing with amperage and time, and in this case, how much chromium is being deposited on the cathode, right? We're making solid chromium. It's an electrolytic cell. We should recognize the cathode is where reduction occurs. So we're going to go from some positive charged ion to a 0. This is going to be reduction. In any case, you didn't have to know what occurs at the cathode. You should have a good feeling for that. But anytime we're figuring out how much is being made in a voltaic or how much is being deposited at the cathode or the anode, okay, we need to know how much current, and that is amperage, okay, is occurring. And what helps in this problem is understanding that amperage is nothing more than the charge due to the electrons flowing through the circuit per amount of time. So how much charge, if we had a circuit, right, and let's say this was the power source here, and if you take a point in time and look at this point here, hey, how much charge is running through that point? Now, the point that we do care about, of course, is at the cathode, or at least one of the electrodes here, to make the chromium in this electrolytic cell using a battery, because it's non-spontaneous. But again, all those pieces of information are not important here. What's important here is they gave me the current. The current is 15 amps, and we should know that means 15 coulombs per second. That's the most important thing. And if you use your dimensional analysis, because they gave me the total time that this current, this circuit ran to produce a certain amount of chromium, I can get rid of my seconds here and get total coulombs. That's really important to understand what you're doing in this step. So right here, we're getting the total number of coulombs of charge. And that might be a point in itself. This is probably a 2-point question, but they want the total number of charge. A unit of charge is coulombs that basically occurred at the electrode where the chromium is being made. The next step is we're going to times it by Faraday's constant to get rid of coulombs. So we're going to use Faraday's constant in the way. And now I know it's 96,485, and I have it written up here. They give it to you this way, the amount of coulombs per mole of electrons. Right? Now I'm going to flip it because I want to get rid of coulombs to get the total number of electrons that were actually passed onto the spot where we make the chromium on electrode. Now, why do I want to do that? Because I know the ratio of electrons to chromium in my half reaction. So once I know the total number of electrons, I can use the ratio of electrons in the half reaction to figure out how much chromium. Then I can do what? Convert to grams. So you can follow that line of thinking. These problems are easier. So the first step is finding the number of coulombs, or the number of charge of all the electrons. Once we know the total charge of electrons, we can convert that to moles of electrons using Faraday's constant. And again, I'm flipping this value here so that I can cancel out my coulombs and get moles of electrons, right? And then the next step is that I want to convert that to moles of chromium, right? Because I know the ratio of, now if I know the total electrons that are traveling to that electrode, and I know the ratio is 1 to 6, I know how many moles of chromium I'm making. And then the last step, of course, here is I'm converting to the mass of chromium here. And of course, I'm using the atomic mass given to us. And every time I'm doing an AP problem, I'm always writing the atomic mass given to me to the hundreds place. In this case, it was 52.00, so you didn't have to, but that's a good thing to do. In any case, you multiply that through, check your dimension analysis. What I mean by that is cancel in a way so that all of your what? Units cancel out. So moles cancel, electrons cancel, and what I'm left standing is grams of chromium. Okay, and when you do the math, you get 4.37. So this is definitely a 2-point question in here somewhere. And it's a nice clean dimensional analysis problem, but understand the flow. Now I've seen the questions go in reverse. Yes, we're reviewing this FRQ that was just released, but understand that the problem can go in reverse. They could tell you that 4.37 grams of chromium were actually collected at the cathode. What would be the amperage? Well, I'd go the other way. I'd convert to my what? Moles of chromium, and going in reverse, I get moles of electrons, right? And then I would use, again, get the total number of coulombs by the Faraday's constant, and then divide by the time, and amperage is coulombs per time. So you can go forwards or backwards here in these problems. Use your units here, very important. Okay, but this is a definite easy problem if you understand the flow. And again, the flow is time using amperage. Amperage is coulombs per second. So understanding that, I'm getting rid of time to get total coulombs. And again, I need to know the charge, and Faraday's constant is a way to go from the charge, the coulombs, to moles of electrons, and then the ratio of electrons in the half reaction. Okay, any case, on to part E of number 2. Question number 2, part E. In a separate experiment, an iron wire is placed directly in a solution of a 0.5 molar dichromate ion with a pH of 1.99. A lot of information here. The concentration of the dichromate ion remaining is recorded over time, and the results are presented. So we've got a reaction. You can see that in this reaction, okay, we see the concentration of the dichromate ion here, and we can see that it's steadily going downward. All right, and it's basically a classic curve for either going to be first order or second order. We don't know which. We know it's not zero order because you should be aware that zero order we would have a straight line if I could draw one, right? Because as you run out of something, it doesn't affect the rate. Remember, the rate, if you had this solve for, the rate is the change of y, which would be the concentration over time, and that would be constant for a zero order. So it's not zero order, okay? But here comes the question. Explain how the data in figure 3, okay, I can do this. Explain the data in figure 3. Support the conclusion that the reaction is first order. So they're coming out and saying it's first order, and they want you to use this data. So if you look at my work, one of the things that screams out to me is that I know that first order curves, half-life stay constant. That's something you have to know. Zero order, as I just drew that straight line, that does not, or second order. And I'll kind of prove that to you with some lines in a second, but you need to know that half-lives are constant in first order. It's one of the ways to identify first order reactions. And how do I know that? Well, if I'm starting with a 0.50 and I have to 0.25, I can find that time to be, or the half-life to be 20 minutes. And if I have 0.25 to 0.125, which would be in between here, I can see that time is now 40 minutes, but the half-life is still the same, 20 minutes. So if the half-life stays constant, we know that this is first order. So that's really the answer. The data in figure 3 supports the conclusion that the reaction is first order due to the half-life of the dichromate ion concentration staying constant for 20 minutes, okay, which is the constant rate. Now let's draw, if I can draw one, I'm going to draw a line here that would be zero order, where the rate would be constant. Now, if we prove this, or at least try to prove this, so let's say the half-life here is, I don't know, let's make it 18 or 17. I'll make it 17. Okay, of course it's got to be a tough number for me. And then we have it again, okay, and well, having again would be right here, and now maybe we're at 26. So that would mean that we would have a half-life originally at 17, and then as we go from 17 to 26, the next half-life would be 9. So it's getting shorter. Okay, so zero order half-lives get shorter. Now if I draw another curve, okay, for second order would look something like this, coming down and then flattening out. Okay, my curve's not great, okay, but we can see that our half-life would be something like, I don't know, half-life, so we're going to get right here, let's make this point here, so 28 would be the half-life, and now because this is leveling off, you probably could see that the next halving, which is going to curve much, much later on, that half-life is going to be much longer. So basically, the half-lives for first order, for first order stay constant, as we should know. Now, for zero order, going straight down here, they get smaller, but for second order, they get larger. Okay, so again, what you need to understand is that first order reactions, half-life stay constant. So I said the data in figure 3 support the conclusion that the reaction is first order, okay, due to the half-life of the reaction staying constant. And I wrote 20 minutes, I didn't need that, but there it is. Okay, so another way to identify through graphs half-life. Now sometimes they give you this data not in a graph, but in a data table, and they'll say, hey, is this first, second, or third order? And if the data table is nice, and it usually is, you can see that do a half-life, find the amount of the original concentration halving, find that time, and then see when it halves again, and if it's staying constant, bingo, it's first order. If it's not first order. You don't have to know that zero order is getting smaller in its half-life as we continue, and then that second order is getting larger as we continue, but you definitely need to know that first order stays constant. One of the ways they do pick on that, and here's a great example. So on to the next question. Number 2, part F, calculate the value of the rate law constant K for the reaction. Report your answer in units of minutes to the -1, so make sure we write those units in. Show the work that leads to your answer. Okay, so they gave us a graph here of the reaction. From a previous question, we've already determined that it's first order, and if we didn't, look at this hint. Natural log of the dichromate ion has a linear line going with a negative slope. This is another example that the previous question is first order. So if you didn't see it based upon the half-life staying constant, boy, the next figure here is screaming to you that this is a first order reaction. Okay, now any case, that being said, they want to solve for the rate law constant. Well, if you know that this is first order, you can identify because the graph with a y-axis of natural log gives you a negative linear equation, we should represent that we're dealing with our integrated rate law formulas, which I have written here. That is how it's written, of course, in our reference tables. And they write them in order. The first one they wrote is zero order, second is the first, and the third they wrote is the second. So they kind of go in order 0, 1, and 2. Now what I did here is I just manipulated this into a linear equation. So I took the first order equation, and then I of course solved for the natural log of A over some time period. Of course, that A of course is the dichromate ion, and I just move that over. As you should recognize that by writing to both sides, what I'm doing is I'm solving for the linear equation, right? So by moving this over, this natural log of A0, I have this is my y-axis, right? Natural log of, in this case, the dichromate ion over time equals negative kT ln. And of course, you should recognize that this is your y-axis. Your slope, and that's a negative straight line, okay? Your time is your x-axis, and your y-intercept is the natural log of the dichromate ion initially. That's what that 0 means. So it's very helpful to see these equations as when you manipulate them a little bit like this, to see them as a straight line, because the slope is your k. So they wanted the k, they wanted the slope of this line, right? So looking at this integrated equation of first order in a linear sense, okay, we can see that we have a straight line. So what I did was I did the change of y over the change of x, and I found two nice points, okay, which of course the change of y is how the natural log changes. So if you look at my graph here, I found these two nice points, all right, where I have my final, right? And then is my initial, and the same thing I have these in red. I have the 9 minutes and 3. So I'm going to use this point here. Well, -1 is my y, and my x is 9 minutes. Okay, and then I'm going to subtract that from my -8, -0.8, and 3 minutes, and that's how I got my slope. And when you do that math, you get k is -0.013. And of course, they wanted the units. So they're not like, accept this answer without the units. They told you that. Report your answer, okay, in units. Make sure you reread these questions, okay? Now, there's, of course, another way you could have done it. You could have used the equation and just solve for k, knowing it was first order because it was a linear line, all right, with a negative slope. And you should be able to understand that's the natural log is a first order way that we identify first orders, or from the previous question, because the half-life stayed constant, okay, we can see that we're going to use this equation here. Now, to solve for k, we need the time. The time between what? Well, find me two intervals. So notice I had 0.8 going to 0.7. So what did I use here is I had the initial point, okay, at -0.7, and then after some time, which was 3 minutes, the value was 0.8. So I used those two intervals, and you could have picked any two. And when you do that and solve for it, you can see that we get the same answer, 0.03. And of course, make sure you put the correct units that they asked for. So that's all that question was. Again, you had to identify that this was the integrated rate law equations that were being used, and this was first order, and using the first order equation, in my opinion, either way works just as fine. Okay, I love when questions have multiple ways to solve an answer. Okay, but again, it really is helpful to understand that these equations, treat them as equations of a linear line. And how do you do that? Just put the a of 0, just using algebra, move that ln of 0 off to the other side of the equation, which becomes your y-intercept. That's your initial part. Okay, so on to the last question here of 2G. Okay, so it says here, the student then runs a second trial of the experiment under identical conditions, but uses an initial concentration of 0.5 molar instead of 0.5. So they're decreasing the concentration of the initial reaction. So the initial reaction is being set up with a half as much molar concentration. So it's a diluted, okay, initial reaction. And what do we know about rate law? Okay, well, rate law, my friends, R equals the K constant times the concentration. Of course, this concentration is going to be of the dichromate ion. I'll just write A. We know it's first order for either the linear negative slope above or the previous question where the half-life stays constant. And so if you have a decreased amount of A, the rate is going to drop, but the K constant is not going to change. Okay, sorry for the K there. The K, or the rate law constant, is temperature sensitive and also sensitive to the activation energy. That's something from the Arrhenius equation that you should understand. So K's, or rate law constant, are not sensitive to changes in concentration. They don't change based on concentration. They change based on temperature and changing pathways. Okay, so the K value wouldn't change, which means the slope does not change. It's just that the initial concentration changes, and that's why I have the same slope. And I took a little bit of effort here, and I think they are too. This is an easy slope, okay, to get to. So I made sure that my slope was pretty much the same. Notice I'm starting about halfway here. If I look at the original, and then I'm going down to like an even number, then almost halfway in an even number. So I did the same thing to really try to make sure that I drew a line that was the same slope. Okay, and then of course I'm starting at a lower concentration. Okay, and they started that for me. Which, by the way, they didn't have to, right? If we knew it's the natural log, we could have taken that concentration and done the natural log to get that value. So yeah, that's why my line has the same slope, but starts lower because of lower initial concentration. Okay, I know it's always easy to see the answers, but that's, again, you must fight to understand what these concepts are. What is K and what changes K? Temperature and activation energy. All right, so in this case it won't change, and of course in this graph K is a slope. So that's really what these questions were after. Do you understand the nuts and bolts of these equations and what they represent, okay, and the concepts behind them? Love the question. All right, so on to now question number 3. So question 3, specifically question 3A, we've got ourselves a reaction, and they want you to identify a conjugate acid-base pair in the equation above. Of course, there are 2, and the word conjugate, if you missed this question, means same chemical. And a conjugate acid-base pair means same chemical plus or minus an H. Acids love to give off H pluses by the Arrhenius, the easiest definition, Arrhenius easiest. And if we want to talk about the Bronston-Lowry definition, acids donate an H plus. So if acids are proton donators, that's what an H plus is, then they're going to have one more proton than their remaining chemical that has one less. What I mean by that is, if you take a look at our HNO2 here on one side, after it does its thing, reacts, it becomes NO2 minus. So that means that these two are conjugate acid-base pairs. The one with the proton, or one more proton, meaning they can have multiple, is the one that's the acid, and the one that has one less proton is the base. So that's one conjugate acid-base pair. Another conjugate acid-base pair, look at the water here, and it becomes H3O plus. What happened to it? It, of course, gained a proton. So that means that this must be the conjugate base. And its other form, same chemical, plus or minus H, this one has one more. So in the reverse, it gives off an H plus. That's why you see double arrows here. Okay, so one conjugate acid-base pair would be HNO2, and it becomes NO2 minus as it proceeds left to right. And as it donates a proton, it becomes a chemical that has one less H, and that's what a conjugate acid-base pair is. So this is one example, or one answer you could have given. And another conjugate acid-base pair is the H3O plus and the H2O. The H3O plus has one more proton, so it's the conjugate acid. All right, and the water, H2O, has one less, and so it's the conjugate base. As simple as that. Conjugate means same chemical plus or minus the H. The one that has one more H, or one more proton, is the acid, and of course the one that has one less is the base. This should be a good review here. All right, so on to question part BI. So in part BI it states, what we want to do here is we want to calculate the value of the hydronium ion, which is the acidic part of water. That is, in my opinion, synonymous with H+. So you think about H+ concentrations, and they're synonymous with H3O+. So when you think about pH, what are we doing? We're going to take that concentration, and it's going to be small because water doesn't dissociate into hydronium ions that much. Its Kw is very, very small, as we talked about. So it doesn't go forward and proceed that much. It's going to be a small number. So to make it something more manageable, we do the negative log, which means we basically take the exponent, a positive value of that exponent, which will be small. Okay, so that's how we get the pH. All right, so now in this question, they want the reverse. They want the what? They want the concentration. Okay, they want the concentration. So how do I go back from a pH back to the actual molarity? Well, we call this the negative log to basically measure the exponent of that number, but you need to do 10 to the negative x back. Sometimes people call it the anti-log. So that's what we're doing here. We're essentially taking our exponent. Remember, don't forget, the reason I started this, the pH is really the exponent. It's 10 to the negative 209. So that's all we're doing. We're putting this back into a base 10 exponent, and then we're going to solve for that in our calculator if you have your caret key working. So that's all that was. It was going in reverse, and it's a basic skill that you should have dealing with pHs and pOHs. So again, all we're doing there is doing 10 to the negative x, and again, it's 8.2 times 10 to the negative 3. All right, and don't forget, that's a molarity. And it's a small molarity. No one wants to deal with those small numbers, so what they do to make this, and it's a convention, they negative log it. Okay, so on to part BII. All right, so part BII says calculate the HNO2 concentration. Don't forget that this is a concentration, it's a molarity at equilibrium. Show the work that leads to your answer. All right, so what do we have? Well, interesting enough, we had this chemical in water already, and we know the concentration of the proton. Remember I said the proton and the H3O+ is synonymous. So already know the H3O+ is 8.1 times 10 to the negative 3 there. That is the equilibrium mixture, and that, if you miss that, then you couldn't do this question. So how do I identify that in part B? They said in part B, I should say, a solution of HNO2 has an initial concentration. Now, it's sitting in water. I always call this a 0.1 question. I think that every acid and base question can be related back to a titration curve. So to me, this is the 0.1. And if you got a titration curve, this to me is where the acid, in this case HNO2, is just sitting in water. And to know the pH of this solution would mean that no matter what the initial concentration is, the pH is going to be how much essentially H3O+ were produced as the reaction reaches equilibrium. They're not coming out and saying it, but an acid or base sitting in water is in equilibrium. Okay, you can't measure the H+ ion concentration just by the initial concentration. It's going to quickly dissociate and get to that equilibrium position here. Okay, now it's a weak acid, so it gets there pretty quickly, but it doesn't matter. So you had to recognize that a pH of an acid and base just sitting in water is at equilibrium. So we know the equilibrium concentration is already 8.12 times 10 negative 3. Now, if you write it yourself an ice table, you can realize that, wait a minute, if we start with an initial concentration of 0.125, and by the way, I have myself a equilibrium ice table, not a stoichiometry ice table, and what goes in equilibrium ice tables are molarities. So they gave us the initial concentration here. And all I'm going to do is essentially figure out what my equilibrium HNO2 is, because essentially that's what they're asking for. So any case, the most important part here was, of course, understanding that this X was given to us. And where did this X come from? Well, it came from how much the initial concentration dissociated into H pluses or H3O pluses. So we know that value. So we know X. So we know plus X. And guess what? Because it's a 1-to-1, we know the same thing as the minus X. So this X is the same X all the way through, right? We know how much H3O plus or protons, remember they're synonymous, okay, was dissociated, right? You just had to recognize that that was in the previous question, was at equilibrium. And if you put that there, it's a pretty simple question. All it really is a subtraction question. So what seems impossible, make sure you say to yourself, what's the easy answer? What's the easy solution to these questions? So I take my initial concentration at equilibrium and I'm minus X. And I know you guys, some of you guys are like robots. Well, don't we always approximate that X? Not in this case. Okay, not in this case, because this actually is a value that's, that can change that. Look at that. 0.125 minus this number here gives me a significantly lower value, right? So we don't always approximate here. All right, any case, we found the X all the way through, and then we subtracted the X. And again, I think writing an ICE table would be very helpful to realize what you needed here. All right, so this is an example of an equilibrium problem where we're going to solve from the bottom up. A lot of times we solve equilibrium problems from the top up, meaning we start with what we have, we find the X's, and this would be the classic case of the Ka is equal to X squared over the initial, and you probably would have to approximate in those scenarios. But in this scenario, we don't approximate because this acid just isn't that weak. It's too strong to approximate. So, and you can check that out. All right. Any case, the answer is 0.117. All right. All it was a simple subtraction. On to part C. Question 3, part C. In an experiment, we have a solution of a 0.125 molar HNO2 is now heated. Okay, so we're increasing the concentration. If you've been with me through the previous questions of part A and B, we've had this reaction where a weak acid is dissociating in water. And in the previous question, we figured out the equilibrium value of HNO2, which was 0.117. Now we're changing the temperature, and now the concentration is a little bit smaller, which is telling us that this reaction equilibrium is now finding a new equilibrium position that's going to have less reactants and more products. So one of those products is H3O plus, the pH would have to increase. All right, if you notice, same idea, H3O plus is 0.0109, and if we go back to the problem previously, we had 8.12 times 10 to the negative 3, so that's a bigger number. So 8.12 times 10 to the negative 3 is a smaller number than 0.01 molar. Why is that significant? Well, because if this reaction is finding a new position that's favoring more products, the Ka, the equilibrium, should be increasing. And you used to say, why? Okay, well, because equilibrium values are measured by an equilibrium expression, which we have here. And it's products over reactants, coefficients become exponents, and solids, and guess what? Liquids do not apply. So when I wrote this equilibrium expression is what we definitely needed to do this. I did not include the water because, my friends, in chemistry, that, my friends, is a liquid. Liquids don't have a molarity, so it's products, right? Here's my products. Over reactants, coefficients become exponents, solids and liquids do not apply. They wanted you to calculate the value of Ka. That's an equilibrium value, equilibrium constant. All right, now I'm kind of talking about what's happening here to set the stage, but I want you to understand what's going on here. So all we have to do is take these new values, since they are at equilibrium, and they have to be to plug them in, we plug them in appropriately to that equation that we just got, and you get 1.04 times 10 to the negative 3. So it's a new Ka. You may say, why am I solving for the Ka if they gave it to me? Because we changed the temperature. Equilibrium constants are temperature sensitive, and that's what part C II is going after in the next question. These questions are linked with the concept. There's a theme to the question. So let's go on to part CII, which kind of runs right into the same idea. Is the reaction represented by equation 1 endothermic or exothermic? Right? Justify your answer by comparing the Ka values, okay, at 298. As I just mentioned, in part CI, we recognize the fact that we now have a higher temperature than the 298 that the original question was after. So they gave us upstream in this question 5.6 times 10 to the negative 4 at 298. We just calculated in part CI that it was 1.04 times 10 to the negative 3. Hey, that's a bigger number. This increased, all right, as the temperature increased. And what does that mean? Well, that means that the amount of products are going up, and we're using up the reactants, and that can be proven, as I just mentioned, by looking at these values in part C and comparing them to part B. Clearly the equilibrium values are increasing, which means what? That means the reaction was favoring the forward direction. And what do you know? You should know this already. This is an important fact and knowledge you have to know, that anytime you increase the temperature of an equilibrium constant, it's going to change, but it changes depending upon if the reaction is endothermic or exothermic. So because we know by increasing the temperature, the Ka increased, which favors more products, we know that we were shifting this or finding a new position that favored more products. And you should know this part. This part is that if you have an increase in temperature, the reaction is going to always favor the endothermic pathway. So if you draw yourself a Le Chatelier's kind of table that I like to draw, and this is my stress and this is my response, if I increase the temperature, the reaction is going to adjust, okay, to lower the temperature. So how does it do that? Oh, by absorbing energy and favoring the endothermic pathway. So anytime we increase the temperature on a reaction at equilibrium, Le Chatelier's principles at equilibrium, then the reaction is going to favor, okay, that endothermic pathway. Well, because it is shifting, the reaction is shifting to the forward. I know that because the products are increasing, then I know the forward must be endothermic. Again, the way to remember that is if I increase the temperature, the reaction's going to respond, that's what the R is for, by working toward a new equilibrium position by lowering the temperature. How does it do that? Hey, it's going to take in the energy. Who takes in, who absorbs? Endothermic. Endothermic reactions always absorb energy. And if you increase the temperature as a stress, the reaction is going to favor always the endothermic pathway. Now, if this reaction caused the Ka to decrease, it did not, just so we understand, if it caused the Ka to decrease, that would mean that we would have greater reactants building up and less products, which is not the case, but I'm just going over this. And that would mean the endothermic pathway would have to be the reverse reaction, because this would mean if we're going to make more reactants at equilibrium and less products, that means we're going to favor the reverse reaction. And so therefore it would be the reverse reaction is endothermic and the forward is exothermic. So a little bit of review here. Endothermic pathways are always favored under increasing temperatures, and therefore exothermic pathways are always favored with lower temperatures. So this is important, okay? So in any case, my answer was endothermic, and I justified, said, but when the temperature increased, the Ka increased. When the Ka increases, the amount of products at equilibrium are increased because an increase in temperature favors the endothermic pathway. All right, so that to me is the best answer. Could you get a little Chatelier's principle in here? Sure. Increasing the temperature is a stress or adding a reaction to equilibrium, and therefore that stress is relieved by absorbing that energy endothermically in the forward direction. Okay, all of that would work as well. So on to the next question. Question 3, part D. So we've got this little blurb here, and we have a second experiment. Remember, the first part of this question 3, we had a weak acid sitting in water, right? Okay, now we're not going to have it just sit in water. We're going to add a strong base. Now this becomes a stoichiometric driven completion reaction. This is no longer equilibrium. I've been talking about that. If we have a titration curve, you can always take any acid-base question and relate it to the points on the graph. So we've been working with point 1, which is just sitting in water before we add anything. Now we're going to drive this reaction forward by adding a strong base. As much base as I add is as much acid that dissociates into its conjugate base. That's important we understand that this is now stoichiometry. Any case, all right, and that's what titrations are, complete stoichiometry. There are a couple of points where there's equilibrium, okay, and the first one is point 1. This question is talking about point 4. Okay, that's called the equivalence point. At least I call that point 4. Going over my points, point 1 is initial. Point 2 is half equivalence. Point 3 is somewhere in the buffer region. Point 4 is the equivalence point, and point 5 is the final pH. Every single acid-base question is based on these points. But in any case, let's get to part D of the question. Using figure 1, which is the titration curve, identify the pH at the equivalence point. Boy, that's just reading the graph, guys. That's low-hanging fruit. So you need to know that this asymptote, the middle of the asymptote, is your equivalence point. That is where the hydroxides that we've added have equaled the amount of acid, weak acid, in the base. And so all we did, of course, is just read the pH at equivalence. We should recognize that pH should be above 7, because what we're doing here, party people, is we're creating a conjugate base, right? This acid is going to dissociate into a proton, and more importantly, into a conjugate base, NO2-1. And because it's a conjugate base of a weak acid, it is going to be strong enough to do what? To rip off a proton, act as a conjugate base and rip off a proton from water somewhere and make the hydroxide and, of course, reform the acid. Okay? Now, that is going to make the pH a little bit basic. Remember, it's not a strong base. It's going to do this a little bit based upon its Ka. So that you should be aware that this pH should be above 7. All right, and I know a lot of people got this wrong. Said, oh, it's neutralized. The pH is 7. No, 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 no. For a weak acid, strong base curve, which you should recognize this to be, the pH is going to be above 7. How do I know it's weak acid? Well, if this was strong acid, it would probably start lower and be a little line that barely moves and then race up. And then the pH, the middle part of the asymptote, would definitely be 7. Okay, just some things we recognize. Even though it's not part of the problem, these are the concepts they're hitting. In any case, the pH is 8. It's the middle of the asymptote is that equivalence point. So on to question part E. Question 3, part E. Using figure 1, calculate the molarity of HNO2 that's in the bottle. Show the work that leads to your answer. So this is a continuing saga of this problem with this weak acid, but now we're titrating. Now we're adding a strong base. Now this is stoichiometry. So one of the things that we do in titrations, one of the major goals, is to understand something about the analyte. What's the analyte? It's the compound that we're testing. So in this titration curve, if you don't understand it, if you haven't done enough labs, understand this. We're dealing with a weak acid that's going to be in some kind of flask, right? And I'll just write HA for simplicity, right? It's HNO2. And then we're going to have some kind of emptying device, usually a burette, okay? And that burette is going to empty something called the titrant. All right, it's not going to be this color, but that's what we're getting here. So we've got a titrant, and we should know that the amount of volume of base added is your titrant. All right, and this is my burette, and I'm going to add some of this as my drops of base. And we're going to add as much hydroxide to this beaker here that we match the hydroxides to the HA. That's what the equivalence point is, right? We're going to keep adding hydroxides, and it's going to be an exponential curve at some point. And then we're going to essentially go past and shoot right past the equivalence point, but the titration curve makes an interesting curve, or an asymptotic line here, where the slope goes to infinity, and we find the middle of that, as we've done in the previous question. We found the pH at the equivalence point. We know the equivalence point, all right, is right here. And so that's an important piece of information. How much base did we have to add to get the equivalence point? Well, it was 50 milliliters. Hopefully you did this in previous labs, and this is awakening, some memories, getting all those cobwebs out and understanding this. So 50 milliliters, I had to add 50 milliliters of this base into this weak acid solution until it's completely neutralized. It was a 1-to-1. And so what I need to know is, well, what's the concentration? So here's what we do here. We're going to take the concentration of the base, which has to be known. It's a standardized solution. It's 0.16. I know I needed 50 milliliters. Now, what's the important part here? I'm going to get the moles here, right? You should know molarity times the volume in liters, in this case it'd be 0.05, is going to give you moles. All right. And moles of what? Moles of hydroxide. And guess what? At equivalence, the hydroxide moles equals the weak acid moles. So once I find the moles of hydroxide, guess what? I know the moles of my weak acid. I guess I'll just write HNO2. And if they want the molarity, how much initial volume? Because now that I have the moles of HNO2, I just divide by how much my what? My volume was initially. Very simple problem, but again, hopefully you did this through your labs. If you didn't, hard to understand. So any case, what I did was, very simply for part E, is I took the 50 milliliters, that's the what? That's the amount of the base needed. It's the equivalence volume. I times it by the molarity. Now, of course, I had to convert this to liters, right? And then I times it by my 0.16, and I got the moles of my hydroxide. And then I said, okay, it's equal to my moles of HNO2. Sometimes I give you a point for that, even if it's implicit in your problem. All right. And then all I did was take that value and divide it by the 35 milliliters that I started the problem with. And you say, where do I get that from? Well, there's a little blurb here. Always go upstream to see what they had. And they said, I take 35 milliliters of the HNO2, that's the substance in my flask under the burette, that's what we call the analyte, and then we're going to add, of course, the base to it. And they told us how much. So all we had to do, again, was divide by the liter. So we found the moles, titration curve, and then of course we divide by the amount of liters, 35 milliliters that we started with, and of course moles divided by liters gives you the molarity. So the initial concentration of the solution was 0.23 molar. So on to part F. Number 3, part F, draw an X on figure 1 to represent a point in the titration. This is the weak acid strong base titration we've been working on for the last few problems, where the what? The weak acid is greater than the conjugate base. Hold on, party people. This is a conjugate acid-base pair. And if you have more of the conjugate acid than the conjugate base, then we must have a buffer. A buffer is a conjugate acid-base pair both present. And this is important to recognize, that you have yourself a buffer problem. And when you have a buffer problem, you should use that Henderson-Hasse block to answer this. Now, if you didn't know it was a buffer, conjugate acid-base pairs do not react with each other. And it's important you understand that, because if you're having a buffer, prevents pHs from changing, which means you have to have both an acid component and a base component depending upon what you're adding to the buffer. And it prevents the acid from, or the pH from swinging one way or the other. The only way to have a buffer solution is to have a conjugate acid-base pair, because they don't react with each other, because they're really components of each other, or they're forms of the same chemical. As strong as the weak acid is as weak as the weak base is. They result from one another. So it's important you realize that. Ka times Kb equals Kw. Any case, so if we have a buffer equation, let's take a look here. Okay, we have, I wrote in here the Henderson-Hasselbalch equation. Now it's important we realize something before we can get to this problem, and I have the answer there as the x, which is below, but I want to explain this further so you understand that. So before I can get to explaining why the x that I put there is correct, I want you to understand that we need to first identify the equivalence point. This is where the hydroxide that we added is equal to the nitric acid that was in the flask. That's the equivalence point, and we found it took 50 milliliters of the base to do that. If I want to titrate the reaction half the way, or to just annihilate or neutralize only half the moles of the acid, I would need half the volume, and that gets us to the half equivalence point. That's important because you should know at that point pH equals the pKa, which is about 3.2, 3.1. I'll just write 3.2 here. It's not important that we put this numbers into the equation. I'm trying to make you understand the equation so you get this right every time. Now, it's understanding that pH equals to pKa when you have equal amounts. Well, why? Because, well, if you have the same amount of conjugate base, that's the top value, and conjugate acid on the bottom, then the log of 1 is 0, and pH equals pK. And if you're going to half titrate an acid, think about that. You're going to add just enough moles of base to drive half the acid into its conjugate base, which means you have half the acid left, and the other half is now the conjugate base. They will be equal. It's a stoichiometric thing, as titrations are. But I'm trying to answer the question here, what would be the pH, or, yeah, I guess I'm really asking what the pH would be if I have a greater amount of conjugate acid. So they want conjugate acid to be greater than the conjugate base. So if I've got a bigger number down here, that's going to make this number, this expression here, become less than 1. And a log of a number less than 1, you guessed it, becomes negative. Right. So if you've got more conjugate acid than conjugate base because we didn't add quite enough base to get past the half equivalence point, okay, you're going to be in this region here. And I'm going to keep drawing this because I call this the buffer region. The buffer region is just right after point 1 and just under the equivalence point. This is where you have both the conjugate acid and base both present. Okay, so any case, getting back to my problem, having more of the conjugate acid means that this number is smaller. Log of a smaller number, smaller than 1, becomes a negative. So this entire expression goes negative. And then you're going to subtract it from the 3.2, and that's why you're going to be a little bit under, right? And that's why you're in this region here. So any x that's below the half equivalence, right? You can't be anywhere touching the 25, and have to be after 0 would work here. And then you should know that anything right after half equivalence and just under what the equivalence point would be where you have more conjugate base, right? So we basically can buffer or create a buffer that's either a little bit above or a little bit below the pKa. Okay, and what scenario would we have this? Well, in reverse, if you had a greater amount of conjugate base, hey, then conjugate acid, that number is going to stay positive, and you would add to that. Okay, for all those reasons, okay, you should get a nice little X to be happening right there because you're going to subtract that. Okay, it's going to be a negative value if you're going to have what? More conjugate acid here, right? That's going to make this number less than 1. Log of negative 1 becomes negative, and we subtract. So again, put the X right there. All right, on to the next question. Question 3, part G. So what we're doing here is we need to calculate the K2 of a certain reaction, and all we have for this problem is 2 reactions above it that we know their equilibrium constants. That means that these two reactions are, when manipulated, will give us the overall. It's the only way it works. We know that equilibrium constants can be multiplied together if the reactions overall cancel out to an overall reaction. It's a lot like Hess law, except we're not going to add delta H's, we're going to multiply Ka's. And there's a reason for that, because you have products over reactants, coefficients become exponents, and solids and liquids do not apply. So when you write the equation for equilibrium constants and you multiply, you actually wind up canceling the chemicals in the equation. Any case, let's get right after this. So what I did here is I rewrote the equations down here. And in order to know how I manipulate them, and then of course figure out what I do to the Ka's for that reaction, right? Whatever I do to the individual reaction I have to manipulate, I also have to manipulate the Ka. It's a lot like Hess law, it really is. Okay, so in any case, if you notice, I need HNO2, that's our weak acid, and I need hydroxide. So if I look at the first reaction, well, there it is, I have my HNO2. Now I also need my conjugate base, NO2 minus, and I have that there in my first equation. All right, so it seems clear that I need the first equation, chemical equation, rewritten as is, and that's what I did here. I just kind of rewrote that, and I wrote down its equilibrium constant there as well. Okay, I'm not doing anything with it because I need it as is. Okay, what else do I need? Well, I need a hydroxide in my overall reaction, and you notice it's in the product side. Okay, so clearly, as my little squiggly here shows, I'm going to flip that reaction. Okay, and so that's what I did down here. Products became reactants, and I flipped it down here. And just to make sure everything is correct, I started canceling. H3O plus cancels. Okay, water cancels, and as you can see, I'm left with the products and reactants. Now, because I had to flip the second one, what did I do with that individual equilibrium constant called Kw, famous for water? Well, I made the inverse of it. Now, why would I do that? When you write an equilibrium constant, whether it's Kp, Kc, Ka, Kw, whatever you want to call it, Ksp, it's got a lot of names for the types of reactions it represents. It's essentially the products over reactants. So when you reverse or go in the reverse reaction, the reactants become the products and the products become the reactants. So therefore you just flip it and we do the inverse. So it was 1 times 10 negative 14 essentially over 1, if you want to think that way, and then I just put the 1 on top. And so I just did the inverse. Okay, which by the way, if you do the x to the negative 1 key in your calculator, that just becomes 1 times 10 to the 14, but I'm just going to keep it that way. All right, so I've manipulated my two equations to get the overall. I've kept the Ka for the first one as is. I did the inverse of the second, and I know that when I'm going to solve for the overall K2, I know I have to multiply. All right. And if you were to multiply, okay, so you take a look down below here, I have the Ka for the first reaction here, and then I have the inverse of the Kw, the second reaction here. And if you multiply them together, you can see that we're going to essentially cancel this, and we're going to be left with NO2 minus as a product. And if you look at your two reactants, when you multiply them together, you have HNO2 and hydroxide. There they are here. Notice there's no water here because the water doesn't get into the equilibrium constants because solids and liquids do not apply. Liquids, of course, are not, do not have a molarity. So that's how it works. So in any case, all we're going to do is take the Ka, which is going to be 5.6 times 10 negative 4. We don't change that because I need that reaction as written. I do the inverse of the second. And if you want to just see, sometimes in a multiple choice reaction, they'll just give you the formula. Okay. In any case, I plug the values in. You do the math and you get 5.6 times 10 to the 10. Okay, which kind of makes sense because when you think about this, the forward reaction in the second reaction, really favors the reactants. So when you flip it, it's really going to favor the products. When you times that by 10⁻⁴, you're going to get a very, very aggressive equilibrium constant that favors the product. That should make sense, okay? All right. One part before we move on, though, what if I needed to multiply something by 2? It's important that you understand that if I needed to multiply something like times 2 here to make something, of course, to make the reactions cancel out, all right, obviously I'd be squaring my Ka, right? It's important you understand that coefficients become exponents. Okay, in this case, of course, we didn't have to do that, but you'll see that in other choices. And it's a really great question to show that things that are on multiple choice questions, which this is a classic multiple choice type of question, can be part of an FRQ. On to part H. Number 3, part H, a student decides to repeat the experiment, this time using an indicator, and has access to the indicators in table 2. The experiment they're talking about is the acid-base titration, where they plotted the change of pH, okay, over the milliliters of base that was added, right? And we got ourselves a classic weak acid, strong base curve. All right, and if I wanted to redraw that, it would look something like this, right? It started low, kind of ballooned up. We had a what? We had a equivalence pH that was about or at 8-ish. Okay, and that's important in this problem, right? This is the equivalence point, and we used the volume for a certain part of the problem, but now we need the pH that we solved for earlier. The pH was 8. And so if we're not going to use a pH probe and plot the pH changes that occur with remember the x-axis is the milliliters of hydroxide that was added, if we're not going to plot that and go past the equivalence point, then we're going to need an endpoint with indicators that change color, guess what? And stop the addition of base when the color changes, right? That's what indicators do. They're actually weak acid base, conjugate acid base pairs that have different colors from their acid to base. But most importantly here is we want the color change to occur where? Well, we want the color change to occur around the equivalence point, right? So we want that around the equivalence point. So if we're going to pick an appropriate indicator, and this is important, that's going to essentially, because it's not going to be perfect, right? It's going to have to approximate the equivalence point, right? So when using an indicator, you want to approximate this position here the best you can. Now you can be off a little bit because this line is asymptotic. So if you're off above and below, you'll still get the same volume. The whole point of the lab is know the volume of base that you have added, so you can solve for what the original concentration of the acid is, or what have you. So that's the whole point of the lab. So if I know that the indicator, or now that I know that I did the first time, if it's the same experiment, I know that the pH will be at 8. Guess what? I am looking for a color change that's going to occur around 8, and there we have enthymol blue in all of its glory. Okay, so that is the one that I want. So a student conducts a second titration, adding 2 drops of methyl orange indicator, which by the way is going to have a color swing, okay, around 3 and 1. Where is that going to be in my titration curve? Well, that's going to be a place where I haven't completely neutralized the what? The acid yet. We want to completely neutralize to understand where this point was, so I can solve for the volume of base needed. So I'm not even getting to that neutralization point at a pH of 3.1 to 4.4. So I'm going to disagree that we're going to use methyl orange here. And what I said here is methyl orange has a color change that's near the half equivalence point, right? But not close to the equivalence pH of 8. Using methyl orange would create an endpoint that does not approximate the equivalence point. The best choice is thymol blue. Okay, because again, its pH color change approximates the equivalence point, and that's what we want to do with color changes, so that we can know how much base was added to match the moles of the proton of the acid, so that we can analyze the analyte, analyze the chemical. So that's where that question comes from. All right, so that's what that question was about, picking the best indicator, which is not very difficult. But I do want to add, though, it's interesting to me that they were using the actual pH ranges. Normally they give you pKa's, right? So interesting, they're using the actual changes. If they give you pKa's approximate the middle position where the conjugate base and the conjugate acid are about equal, and that would give you a good indicator where the color would swing to. All right, so in any case, definitely disagree. Thymol is better. You're not going to approximate the equivalence point. You won't be able to gather any data that's going to accurately depict what's in the analyte or the nitric acid based upon how much moles there is, okay, with that indicator that they picked. On to question 4. Question 4, the white phosphorus question. They say it can decompose into P2, elevated temperatures. They give us the bounce reaction. They even gave us the equilibrium expression using the partial pressures. And we have 2 Lewis dot diagrams here. And here comes the question. The average bond length in P4 molecules is 221, whereas the average bond length in P2 molecules is 189. Explain why the average bond length in P4 is greater. So why is the length, the distance between the bonds here longer between the P4 molecules than it is between the P2? That's essentially the question. And there's an important relationship, and I kind of have it written down here a little bit. Bond energy is inversely related to bond length. The energy needed to separate and break a bond is inversely related to the length of the bond. And this should be pretty intuitive if you didn't quite pick it up, and maybe that's why you're here. By them telling me that the average bond length in P4 molecules is 221 and that of P2 is 189, clearly, okay, has something to do with the extra bonds between the P2. It's got to be the answer, and it is the answer. If there are more electrons being simultaneously attracted, thus the bonds, between the two P atoms, they're going to get pulled in tighter. So stronger the bond. Now, what is a covalent bond? Well, it's 2 nuclei simultaneously attracting electrons. So think about 2 nuclei, 2 positive nuclei attracting electrons. The reason they say average bond length is because that bond length does change quite a bit. So the average bond length is a distance where the attractions between the electrons are maximized and the repulsion between the nuclei are minimized. So they're about as close as they can get before they start repelling. And that's that famous diagram that we see, that internuclear distance diagram, where we have energy plotted here on the x-axis, and here is the lower energy spot or the stable position, and this of course would be the bond length. Stronger the bond, deeper you go, and normally closer or shorter. So as we add more electrons to the mix here, that means there's more for the nuclei to attract and they get pulled in tighter. So I just basically said here, the average bond length in P4 is greater than the average bond length in P2 due to the 2 additional pi bonds. You guys should recognize the first bond, when I say first bond, I say the bond, the single bond that originates between these two is a sigma. The sigma is a direct overlap of orbitals, and that creates electron density right in between the 2 nuclei. All right, and then of course in pi bonding, we're going to have unhybridized p orbitals that are going to provide even more electron density between them. They're not quite as strong as a sigma. And then of course we're going to have another, in this case, another unhybridized orbital in another direction. And that'll be like front and back. So we go top and bottom for one pi bond. And then we'll change the color here, front and back for the other pi bond. So as you have more electrons, even the little weaker pi bonds here, as you add more electron density between the nuclei, which you can think is right here, they get pulled in. All right, the nuclei get pulled in a little bit. okay, because both nuclei have more to attract. So again, so higher the bond energy, that's the energy to break the bond or strengthen the bond, okay, shorter the bond length. And that's what that internuclear distance diagram was teaching you when you guys were learning this. Again, I have a little sloppy one here, but you know, if you think about energy and this being the distance, okay, if we have everything being the same, meaning we're not changing the atoms, we're going to add an extra bond, well, this would be deeper and the bond length would be shorter. So the distance here would be shorter. Okay, so you've seen that before in this course. You just didn't see it in this question if you're here reviewing with me. So it's not a big deal. All right, so that's all they wanted there for part A. So on to the next question. Question 4, part B. A sample of P4 is placed in a sealed rigid container and heated to 1600 Kelvin, at which point the initial partial pressure is 0.47 atmospheres. Some of the P4 decomposes into P2 from the reaction they gave us above, and I kind of wrote that right here. So some of that goes forward since they're starting us with 100% of the P4. They gave us that initial concentration. And then the system reaches equilibrium. That's an important part of this. Okay, once it reaches equilibrium, we know the P2, that's the product, becomes 0.63. So we know it becomes 0.63. Now, if you notice, I didn't write it there. And because I kind of want us to teach this to you in a way that you can see that this kind of question is called I call it a bottoms up equilibrium problem. Many times we solve equilibrium problems where we're gonna, you know, given the K, P, or the KSP, whatever value of K that would give you, we solve for one of the X's and we go on from here. Here they're giving you the value of X. And then we're going to kind of work backwards to get some other value in the table. So the table is kind of helpful. And by the way, this is a equilibrium table that I have here. Okay. And so what they gave us was the initial concentration, not at equilibrium. And by the way, this is concentration. So these are molarities that go in an equilibrium ice table. If it's a stoich table that I love to use, it's moles. I always assume I have 100% of the reactant and 0 products. That means it's going to go forward at some point until it reaches that equilibrium position where everything stays constant because the rate of the forward equals the rate of the reverse. And we're going to be minus X here, and we're going to be plus 2X. That's the key to the problem. Notice the coefficient of 2 here. So whatever molarity is lost as a reactant as this goes forward, we double that for the P2, all right, because of the stoichiometric relationship of 1 to 2. That's important. And so when we get to equilibrium, it's going to be 0.47 minus X because we're going to lose something. And of course, this is going to be 2 times whatever X that was lost. Except they told us that value was 0.630. So 2X equals 0.630. Now, the question is asking, calculate the value of the equilibrium concentration Kp for the reaction at 1600 Kelvin. Now, to answer that, and they were very nice to give you the expression, all right, to remind you that there's a square here because products over reactants, coefficients become exponents, solids and liquids do not apply. Notice the parentheses in the P for a partial pressure if you ever have to write that. But in any case, I know the 0.63 already. I know that value. They gave that to me at equilibrium. We have to figure out what the value of the P4 is. We started at 0.47. We know it's going to go forward a little bit. How much of that is going to decrease as it goes forward? And so the value or the amount that it goes forward depends upon the X. And because they told us the value of 2X, which makes this a little tricky problem, I have to divide by 2 here before I subtract. So 0.630 partial pressures. By the way, I might have said that molarities go, or concentrations go in a equilibrium table. That's true, but I forgot to add, like in this case, you add also partial pressures. Any case. So we divide our 0.630, which is the equilibrium product, amount of product, we're going to divide by 2, and we get, of course, we're going to take that value and subtract that from 0.47 because it's going to lose something as it goes forward. So take your 0.63, divide by 2. Now that's your value of x, and now we can solve for x. Now I know some people are saying, wait a minute, I thought we always approximate that x. No, we don't always approximate that x. Be careful. Don't be a robot and just always do things because you recognize that's the way that we have been doing some other problems. Think on your feet here. We approximate this x away if we're trying to solve for x and we're dealing with a very, very, very small Ka or KSP, because this x will be tiny compared to this value. You don't know what the value of Kp is. Okay, we know it's going to be subtracted by some value. We can't assume that it's insignificant since they're asking for it. So just be careful about that. And by the way, there's a general 5% rule. When is the Ka, the KSP, or any value of K small enough that this x that's being subtracted away from the original concentration is in fact insignificant? It's about it's a 5% rule. So if your x that you're subtracting is smaller than 5%, you could approximate that away. But in this case, you don't know that. It'll wind up being much bigger, as you can see. All right. So any case, because 4.7 is going to 4.39, it's clearly significantly being altered here. Okay. Any case, so I'm going to subtract the half amount of 0.63 from 4.7. And I get 4.39. And then of course what I do with that is I plug that into my equilibrium expression, right? We put the 0.630 here, and now we're taking this value here. Don't forget to square. Coefficients become exponents, right? And then you solve to be 0.0904, which looks to be a small number, but it's nowhere near like the KSPs that like 1 times 10 to the negative 8. That's extremely small. This is actually pretty big in comparison speaking. Any case, I believe this will probably be a 2-point question for attaining this value for using the stoichiometry and understanding that's 2x there in your equilibrium table, and then another value for appropriately calculating the right answer. That's my assumption there. Okay, so again, I call it a bottoms-up question where you're using something at equilibrium to solve for something else, or in this case, solving for the equilibrium constant. Often we get the equilibrium constant and then we solve for the value of x. So it goes one way or the other. Interesting enough, this is I believe the second question where we had a bottoms-up type of question here. Okay, on to part C. Number 4C, the very famous thermodynamic favorable question, when you're given values of enthalpy delta H or entropy delta S, and you're trying to determine whether temperature and how it plays a role in the Gibbs free energy or the delta G, whether it'll make it spontaneous or not. So I always think when I see these questions, always think math, right? We know delta G, if it's going to be spontaneous, is negative. So the reaction is thermodynamically favorable. That's what we're reading here. That must mean that it must be negative. No if and buts about it. That must be negative to be spontaneous. Okay. And it's only at temperatures above 1500 K. Well, that's giving you an important clue. That clue that that temperatures is causing it to be spontaneous, whether it's an increase like this question or a decrease, screams to you that you have this scenario where you have one of the two favorable conditions, right? So one of the favorable conditions is, we should know, is entropies that's increasing. That's the entropy or the degrees of freedom. So if delta S is increasing, we say the degrees of freedom from reactants to products are increasing, whether we're going from a solid liquid to a gas, or 3 molecules or 3 moles of reactants to, let's say, 5 moles of products. That increase in disorder, randomness, or dispersion of energy, however you want to think about it, is increasing. That's a favorable condition. That's a fave, because we know that Gibbs free energy, or free energy in general, is a measure of spontaneity, because we know it's a measure of the entropy of the universe that must be increasing, right? Delta S of the universe. And there's two parts. There's the internal system that delta S measures, and there's also the surroundings that delta H is tied to. Okay, so what's another favorable condition? Well, that's if we have delta H that's exothermic or negative. So if we've got a condition where we're going to have some system in a box here where the chemical reaction is going to occur, and inside the box the degrees of freedom of reactants and products increases, that would be a favorable condition. That means the entropy of our system in the reaction container is increasing. And if energy is being released, not sure what my voice is cracking there, but if it's being released, then we know that the surrounding entropy of the molecules in the air or the outside container or the surroundings, right, is increasing, because at higher temperatures they wiggle, they move, they translate more, and they can move away from each other. They get less dense. All those things lead to an increase in total entropy. So these are the two favorable conditions. And when you have both of these, exothermic and your delta S of your system becoming positive, then you're always spontaneous. And if you have the unfavorable conditions, which means we have endothermic, that means energy from the surroundings is going into the system and you're getting colder, and that means things are moving slower while the entropy of the surroundings are decreasing. And another unfavorable condition would be for the delta S to be negative, which means you're going from, let's say, a gas to a liquid or a solid. You're becoming more ordered and structured, or you're moving slower, or you can say that, you know, things are coming together, like 5 particles are becoming 1. All right, so less degrees of freedom. So in the case we have temperature being involved, we know we have one of the two. All right, so let's get back on this. So we know it's delta G is negative. Okay, that's important. And the claim is that the reaction must be endothermic, okay, because it's favorable only at high temperatures. Do you agree or disagree? Okay, if it's only favorable at high temperatures, that's really a key here. That means only is the temperature high enough to make the back part of the equation big enough to make this value negative. Now let's stop for a second. Use the math. First and foremost, if we're going to say it's endothermic, and that's the claim, that's an unfavorable condition. That's right, unfav here. That is not a good sign, but we can overcome that. There's 2 parts of the entropy of the universe. There's the delta H and the delta S, or 2 parts of delta G. Now, if this was also unfavorable, it would never occur. You can't have both the entropy of the surroundings by delta H absorbing energy and the entropy of the system both being decreased. Okay, it never becomes. So they said only at high temperatures. So the point here is that I know that for this to work, for this to be negative, for delta G to have a chance to be negative, we need a positive sign for delta S. Okay. So the delta S, that's why they say justify your reasoning based on the delta S of the reaction and the delta G of the reaction. So if this must be negative and it's endothermic, hey, this must be positive. Okay, and so we have what we call a favorable condition for delta S right there. Very favorable condition. Now we have a good condition here and a poor condition here. So if delta S is favorable, which means we're increasing the entropy of the system, how can I overcome this unfavorable condition where the entropy of the surroundings is decreasing because heat is being taken from it into the system? So we can maximize this favorable condition by increasing the temperature. Now I'd rather say the following. I'm going to get rid of all of this again. I'd rather, again, do the math. So if delta G has to be negative, all right, if it has to be negative, and this is endothermic, well, this must be positive. It's the only way that you could ever have. Do the math. A positive minus a positive means that this value of this negative can occur as long as this positive value, with, don't forget the negative in front, is big enough to overtake this positive. See what I just said there? With this positive value, if it's big enough, remember the negative is here, so overall it's really a negative expression, but if this T delta S part is big enough, which makes it what? more negative to overcome the positive value of the entropy, this becomes negative. So way to say that is, I said I agree. All right, if a thermodynamically favored reaction, negative delta G, there I am talking about this, is endothermic, delta H is positive, then the entropy must be positive with high temperature to be an entropy-driven reaction. Entropy-driven just means that your entropy of your system is high enough to overcome the loss of entropy by an unfavorable enthalpy of delta H. In order for delta G to be negative with a positive delta G, the delta S direction must be positive. The only chance you got is that this must be positive, because if it was negative, it would not work at all. You could never get a negative value. It would just be positive. And so I'll say it again. So in order for the delta G to be negative with a positive delta H, that's the claim, delta S of the reaction must be positive with a large enough temperature so that what, here we go, here's the winner right here, T delta S is greater than delta H. And again, why? Because of that negative right there, right? So if you make this T high enough, this becomes a larger negative with this negative sitting in here. And that can make this overcome whatever size positive that is to make the delta G negative. Okay, so I would use the math. In this case, we're looking for T delta S. A high enough temperature is going to make T delta S greater than delta H, which is going to make sure delta G is negative and spontaneous. All right, so on to question 5. Question 5, part A. So we're given a Lewis diagram of this molecule, and they're saying in the question which of the bonds in the CbClF2, C to Br, all right, C to Cl or Cf is the most polar. Okay, now make sure when you hear the word polar, you remind yourself, are we talking molecular bonds? But they're specifically asking about the bonds. And when you've got yourself a polar bond, you have unequal sharing. So one of the things, if you got confused here or didn't understand the concept, if I was to draw a carbon to fluorine bond, there's a pair of electrons that exist between them. That's what that dash means, right? So this dash right here represents a shared covalent or bond. In this case, it's sharing unequally. Now, why do I say that? Well, the electrons that are between here are going to be pulled closer to the fluorine. And the reasoning is because fluorine is more electronegative. Now, I inserted or put to this key your reference table, or at least your periodic table, and you can see where fluorine is. So fluorine is up to the right, and the general trend is to the right and upward in the periodic table. You have the most electronegative atoms. Of course, we do not include the noble gases. They are something that we would cancel out here because they we can't measure their electronegativity because they don't tend to bond. So we kind of exclude them from that kind of talk. So the element that is toward the right and upward is fluorine. This is the most electronegative atom. And you should know your trends as you move upward on a group or a family of elements. The size of the atom becomes smaller, and therefore the proximity of its nucleus is more exposed to other electrons. Remember, electronegativity is measured by how well the nucleus of an atom in a covalent bond can attract and pull on other electrons that it does not have. So you need to have a nucleus, its nuclear charge high enough, but it has to be small enough to be able to create this positive field to pull in electrons. Bigger atoms have a tougher time because that nucleus is so much, buried underneath layers of electrons, principal energy levels and shells, and as you add more shells it gets deeper and that distance decreases. So it's really Coulomb's law that the distance is small enough that the nuclear charge can have effect on the number of protons. And you have to have, of course, a larger number of protons. That's why the nuclear charge, as that increases, so does electronegativity. And of course, size, smaller atoms expose that proton or those nuclei of protons that are positive more so to other elements' electrons. So because of that, I said the CF bond is the most polar, and it's because you understand it's sharing the most unequally, because the fluorine atom is the most electronegative atom of the Br, Cl, and F. Electronegativity increases as the atomic number decreases. That just means I'm moving up a column. And now, if you're still kind of lost about this concept, and hope that you're not, if you draw yourself a box between the two elements, think about fluorine, as I said, pulling this pair closer to it. That's why I drew it, that pair closer to the fluorine, which we're going to have to understand later in other parts of this question. But what's more important here is that because there's more electron density on this side of the bond, we would say this side of the bond has that partial negative sign. And because the carbon has less electron density as the electrons are, pulled closer to the fluorine, then we would say this is a partial positive side of the bond. Right? So we've created differences in electron density that creates the polarity. All right. So in any case, fluorine is more electronegative. You don't have values. You have to read and understand the periodic trends as I just explained. All right. So in any case, on to 5b. Number 5, part B. Now this question here really ties into question 5a. If you're with me just now, we talked about that fluorine was more electronegative. What that means is it pulls on the pair of electrons and pulls them closer to the fluorine. And that's the key to this problem, using electronegativity differences. Okay, and of course understanding something about VSEPR theory, valence shell electron pair repulsion theory. Atoms make shapes, the three-dimensional shapes they make, I should say molecules make shapes, the three-dimensional shapes, by looking at the central atom and looking how these electron densities in these orbitals that are emanating out from the central atom, how do they repel each other? These are electron densities, these are orbitals, these are waves of probability, whatever you want to talk about, but there's electron density in these shapes. And negatives do what? They repel other negatives. So that's the shape it takes. So the question states, in a molecule that we have here, the fluorine to carbon to fluorine bond, and that's the bond right here, has a bond angle that's 106.8. Now that should ring a bell to you, like, wait a minute, this is a four-sided tetrahedral sp3. This should have 109.5. So there's the bond angle here is smaller than 109.5. You should know 109.5 is the bond angle in a tetrahedral where the orbitals have all the same density. When we say sp3, an s and 3 p's, mixed together, they gave the same density. But okay, as this question is showing you, that's not always going to be, the electron density is not always going to be the same depending upon the electronegativity of the atoms. But in any case, let's get back on it. And we know that the Br to Cl bond, okay, that's, I guess I have two Cl's here, so I should have one of these Cl's be, I can fix that, be Br. Okay, if you're screaming at me, wait, where's that Cl came from? Okay, so this Br that I just added, the Cl to Br bond here, okay, is 112.3. which is much bigger, or at least bigger than 109.5. So what gives here? Explain the difference in bond angles using principles of atomic structure. Okay. And VSEPR theory. Okay, well, things to explain for me. Well, number one, and looking at this question again, and I've looked at it several times, and I think I come up with something new almost every time, but the best answer, I think, is that because fluorine has greater electronegativity than the chlorine and bromide. So that's something you need to say, is that number one, fluorine has greater electronegativity than the chlorine and bromide. We've kind of said that in part A and established that, so I don't think you need to restate that. But you need to understand that because of its electronegativity, right? Why does it have a great electronegativity? Well, because it's a smaller N number. Fluorine exists as a smaller atom. Okay, that's one. And it has a nucleus that can attract electrons better because of that, and it has a high number of protons. So when they say principles of atomic structure, I really think you need to bring up the fact that because it's more electronegative, all right, or that it's a small enough atom with a great number of protons, okay, struggling here because I think this is an odd question. What it does is it lowers the electron density in the region near the carbon. Notice how I drew the orbitals, the sigma bonds, I should really say, right here and here. Look how skinny I have them near the carbon. That's because fluorine did what? Fluorine basically pulled the electron density away from the carbon and created these skinny areas right here. All right. Now, chlorine and bromide don't have the same electronegativity because they exist down a group, right? They have more filled shells of electrons that essentially make it harder for its nucleus to attract other electrons. It's lower electronegativity. That's where the atomic structure is coming from. So this is going to have a richer and a bigger electron dense region. So this is where I think they're going with it. I'm not a big fan of this question, but any case, because of that, because of more electron-rich region, these more negative regions can repel these smaller negative regions more. These regions are not all the same, okay? And of course, you can also make the statement that the fluorine here is not going to repel itself as much because there isn't much electron density in this region here. Remember, it's by the carbon that creates the shape. So for all those reasons, fluorine is going to have less repulsions between itself, and the thicker, bigger electron negative regions near the carbon here from the less electronegative atoms are going to repel and push the fluorines toward each other, which gives them a much greater bond angle. So what I said was the FCF bond is smaller than the expected 109.5. You didn't have to say that. For the molecule, because the two fluorines, which are more electronegative than the Br, create very polar bonds that attract most electrons away from the carbon. Less electron density near the carbon atom results in decreased electron repulsions. Now, this part here, I think, is what's needed for atomic structure. The difference in electronegativity, size of the atoms, number of protons, comparatively speaking. Okay, but this part here is where I need to talk about VSEPR theory, how these electrons repel themselves. Well, if you've got more negatives, a richer negative region is going to have a greater ability to repel other negatives that have less and a lowered amount of electron density. So I said less electron density near the carbon atom results in decreased electron repulsions, while the greater electron density near the carbon and the BCl atoms experience greater repulsion and thus a larger bond angle. Okay, so I think there's many ways to say that. Interesting to see what they come up with their key. It's never really interesting to read their keys because, well, they kind of give a one or very simple answer, but it'd be interesting to see if we could see all the ranges of things they accept for this. But clearly there's less density in these regions here, and therefore they repel themselves less. More electron density here because of less electronegativity, and they're going to repel more, and that creates the differences in the bond angle, something along those lines. Okay, and I don't think you need to talk about electronegativity again, but if you do, to me, you're using those principles of atomic structure. All right, so on to part C. Number 5, part C, we've got our intermolecular forces of attraction question. They're giving us boiling points, and they're giving us Lewis dot diagrams, and they're asking us to identify all the intermolecular forces here. I always tell my students, always in these questions, identify all the forces. Here they're just coming out and saying it. So this is definitely a 1-point question, I believe, to get all of these right. And I can see that CB4, okay, is a very symmetrical molecule, or its dipole moments cancel. This is a nonpolar molecule, so it can't have any H bonding. It doesn't have any hydrogens to begin with. It's not polar. So CBr4 only has London dispersion forces, which you should be aware is just due to the cloud of electrons surrounding the atom and how that cloud distorts when it's around other electrons and repels. So this entire question seems to be about electrons and how they affect other electrons. Okay. Now, that's important to understand because the next molecule clearly is polar. Okay, clearly it's going to have a negative end here. The partial negative is going to be the fluorine side in this tetrahedral sp3 molecule. Now, of course, the fluorine side is going to have more electron density, so it's going to be polar, but you have to also remember that this has a cloud of electrons too. All molecules, polar and nonpolar, have London dispersion forces, right? So it does have a cloud of electrons. So don't forget, just because it's polar, when you think about intermolecular forces, think about the collective amount of the different forces a molecule has with itself, or let's say with a solvent like water, to describe it. So how would this molecule attract itself? Well, it's going to attract itself by the distortion of its cloud. It has electrons, and it's also going to attract itself by the permanent, I say permanent because London dispersion forces, or LDFs, don't have permanent dipoles. There's just how the cloud interacts with another cloud, if they're close in proximity, will create the momentary negatives and positives. Whereas a polar molecule is going to have the permanent negatives, okay, and positive areas. Any case, this has two forces. It has London dispersion forces and dipolar forces. And normally, when you add an additional force, that usually means that you're going to have a collectively, greater overall intermolecular force of attractions. Don't forget that when we talk about IMFs, intermolecular force of attraction, it's a collective sum of all of them. So if I was to ask you, without seeing these values, right, which one would have the higher boiling point, which one would stick together and attract itself more, you probably would say that. Okay, and that would be a great answer, because it has an additional force that the other one doesn't. You wouldn't have any other recourse but to answer that way. But what they did here is they gave you the scenario with CB4 having a higher Kelvin, and then they want you to explain that now, okay, in the next question. So this was question 5C here. Just want you to identify the forces. Don't forget, all molecules, polar and nonpolar, H bonding or not, are going to have LDFs because they have a cloud of electrons. Question 5CII, in terms of the relative strength of all intermolecular forces, make sure you read the question. So in terms of the relative strengths, they're screaming to you how to answer this question. Explain why pure CBBr4 has a higher boiling point than pure CbClF2 liquid does. Now, again, as we said before, CBBr4 only has LDF forces, but somehow it has a higher boiling point, which means it must have stronger intermolecular forces of attraction. If it's sticking together stronger than the CbRClF2, then it's going to need more heat to overcome those attractive forces and escape as a gas. That's important you understand that. Stronger the intermolecular forces, the higher the boiling point, the more energy you need to vaporize, right? That's something you need to visually understand, intuitively understand. Somehow, CBr4's single LDF intermolecular force must be somehow larger than the combined two forces, LDF and dipolar forces, of the CbRClF2 in order for it to stick together more strongly and require a higher energy and a higher boiling point. All right, so that's the key there. And to me, to explain, you should say why those LDF forces are so strong. So I said CBr has a higher boiling point than the CbRClF2 because CBr4 has stronger LDFs than the combined LDFs and dipolar forces of CbRClF2 due to CBr having more polarizability. I probably should say that or being more polarizable due to having a greater number of electrons in its electron cloud. Don't forget that LDF forces increase the closer you get. They increase with greater number of electrons. They increase with more delocalization of electrons, and they also increase with the shape is less branched so that the cloud can distort more. So in this case, LDFs in CBr has more electrons. And why? Well, because bromide has a greater atomic number than the fluorine, okay, or the chlorine. So having 4 Brs surrounding the carbon has a greater number of electrons. All right, so that's the answer there. So that's what they were after. Normally, hey, having more different and combined intermolecular forces usually leads to a stronger intermolecular force attraction. Here's a case where it didn't, and I love this case. It comes up quite often where you're going to explain that the LDFs were strong enough to, again, be collectively stronger than the combined forces of the other two of the other compound. All right, so on to number 6. Question 6, the spectrophotometry question. So what we've got here is a Beer's law graph or a calibration curve, whatever you want to talk about, but it's showing a linear relationship or a proportionate relationship between the molarity and the absorbance of some colored, okay, solution, some solution that produces some kind of color that is absorbing part of the probably visible spectrum. And absorbance, you should recognize, is the amount of light that is being absorbed by the chemical in a solution, in a cuvette, in a spectrophotometer. It's the missing light, right? We shoot a known amount of light through a cuvette, and the detector picks up how much is coming through after you calibrate it with no light. So this means that there is more missing light on the detector because more of the chemical is absorbing it as the concentration goes up. So how the lab works, and you should be aware of that, we take known values, known molarities, and we measure the absorbance or the missing amount of light that's going through the cuvette in a spectrophotometer to see how much of that chemical is still there. It's so important you understand this. Okay, so if we have ourselves a cuvette, I'm just going to draw a triangle here. And of course, this is what we put our colored solution. And I'll just put a couple of dots in here to recognize there's the molecule responsible for the color of the solution. And we're going to shoot some visible light through here. I'll do that with some yellow maybe. So we're going to shoot, we have some kind of white light source that has a decent amount of full spectrum, and we shoot that through the substance. Now, some of that light is going to be absorbed by this chemical. The reason why it has a color, because essentially electrons are in these chemicals are able to absorb certain wavelengths of these photons and get excited based upon their electrical arrangement, and not all the light hits the detector, right? So probably a better way to do that is I'm shooting light, and I have a detector here, and only some of it goes through, and that depends upon how concentrated the solution is, what the molarity is equal to. If you have less of these or have a lower concentration, well, then more light of a certain wavelength will get through the detector, and there's less absorbance. So what we're measuring is how much missing light. We know how much light is supposed to hit the detector based upon an empty cuvette when you calibrate, but when you put the substance in there of a certain color or wavelength that it absorbs light, some of it gets absorbed. And as you increase the concentration, more of that light gets absorbed. Therefore, there's more missing light, and there's a greater absorbance by the chemical. So there is a certain proportionate relationship that we need to understand here that's occurring. and this has a linear equation, but it has an important equation that we need to talk about. And it means absorbance, that's the light that the chemical is taking from the source, or the missing light, is equal to an absorptivity constant that is unique to each spectrophotometer, times the path length, that's the length that the light travels through the cuvette, and of course times the concentration, which of course is the molarity. And so this distance the light is traveling through the cuvette, through that rectangle, is constant, so of course is the absorptivity constant. So if you've got greater concentration, you've got a greater amount of absorbance of wavelengths of light of a certain type of the chemical in the cuvette, or hey, there's more missing light. So this is the relationship that we're plotting here. Okay, so we take known concentrations, we plot them, we get a linear line, and then we have an unknown sample. So what they're saying here in part A is that now we have an unknown sample, and we measured the absorbance to be 0.32, and we could get the concentration from that. Okay, but they're not going there yet. So we're going to use this curve to essentially answer what an actual molarity of an unknown sample is, knowing this relationship, this line. But we're not getting there yet. So in part A, they want you to draw a diagram. So take a look at this. So they're giving you this diagram first. And they're saying that, hey, if we have an absorbance of some unknown solution of vanadium that's 0.32, if I give you this diagram with molecules, which is basically giving you a molarity. Molarity, of course, is a ratio of the moles of the dissolved solute. In this case, it's the vanadium plus 2 over the liter of solution. So the liter, or the volume, is this circle. That's the area. And the mole, of course, is how many of these vanadiums. So I counted for you 1, 2, 3, 4, 5, 6, 7, 8 particles. And that's what I have here. And notice I have my formula, A equals ABC, except sometimes I write that A as this funky E here for the absorptivity constant. But the bottom line here is that they're getting an absorbance of 0.32, and they're giving us 8 molecules per this circular volume. All right, now what they want to do is they want you to draw the correct number of vanadium ions to represent the concentration of a solution that's 0.08. All right, now think with me for a second. They're giving you this at 0.32, and now they want you to draw it for 0.08. Do you see a relationship here? Well, yes. The concentration has to go down if the absorbance goes down. Because it's a direct proportion here, as we just see here, what would be the number that we have to draw? Well, if you do the ratio, and here's my answer here, if you do the ratio, and I just did the ratio of the absorbance concentration, when we had 8 particles, okay, it was 0.32. If it's 0.08, wait a minute, 0.32 or 0.08, hey, that's decreasing 4 times, or a fourth. What's a fourth of 8? 2. And that's why I draw 2 particles here. All right, so if the absorbance goes down from 0.32 to 0.08, the absorbance is going down a fourth. Hey, the concentration, which is molarity, goes down a fourth. Remember, what's concentration? Hey, it's moles over liter. They're giving me the same what? Volume as this circle here. I know it's an area because you don't see the depth, okay, but it's two-dimensional drawing, but that's the same volume, so the moles are going to go down, okay, a fourth. What's a fourth of 8 particles? Of course, 2. All right, so that's all they were doing here if you got stumped. They gave you a nice number. 0.08 is a fourth of 0.32. They gave you 8 molecules of 0.32. Hey, has to go down. And of course, the reason why this works is because of this formula. Absorptivity, or absorbance, is proportionate to the what? The concentration. All right, remember the path length and the, of course, absorptivity constant stay constant. So that's all that is for the question. A fourth of the 8th is always an easy answer to all of these questions. Okay, on to number 6, part B. Number 6, part B states that a student measures the absorbance of a different vanadium solution with an unknown molarity. That's what we're trying to figure out. But the absorbance is higher than the 0.36 upper limit of the graph. Now what that means is they can't use the absorbance, okay, of that graph with this concentrated vanadium solution, right? So the curve that they have has a certain molarity limit. So they're going to dilute it and then use a way to understand what that current molarity is. So the student then transfers. This is important here. The student transfers 3.0 milliliters of this vanadium solution to 25 milliliters volumetric flask. Volumetric flasks are used to measure concentrations. It's worth drawing the flask because as I go over this, I'm reviewing other questions. Volumetric flasks have a particular shape and they have a particular precision to them. This precision is this little tiny line that gives us exactly what the volume that we're trying to make the solution for. There are 1 liter volumetric flasks. In this case, we have a 25 milliliter volumetric flask because remember, molarity is going to be mole over liter. So we want to make sure that our volume of our solution, okay, is as accurate as possible. All right, so any case, what we're going to do here, so follow along here. Let's go back. You had to read this. This became more of a reading question than a chemistry question. So student measures the absorbance of a different solution with an unknown molarity, but the absorbance is higher. It's higher than the graph, right? So therefore, they want to dilute it and then read the absorbance from that diluted value. And then from that absorbance, from that diluted solution, use the curve that we have to get the concentration. And that's what they want for part I. They want to know what that concentration of that diluted solution is from your graph. So they're saying the absorbance in part BI is 0.22. So what is the molarity from that calibration curve now that we can use it because it's diluted? So if you go to 0.22 or we find 0.22 on a graph, I would rather you use y equals mx plus b as we've seen in other problems, as you probably did in your lab. But in this case, because well, it's just easy to read from the graph because the points are really nice, right? If you look very carefully, look how nice these points are, right? So we have, these are going by 2. So 2, 4, 6, 8, 10. So 0.22 is right on this line here. So I made a dashed line and it hits right on the value of this line or this grid here that's 0.055, right in between 0.05 and 0.06. So it gives you a nice line. So there is my 0.055 right in between there. So they give you a nice point to read from, which is definitely appreciated based upon other graphs they may you do that from. So in any case, scrolling on in, that's your answer. So you're just reading it from the graph. Okay, so part BII now. This is connected. And so now they want you to determine the molarity of the original undiluted solution that was, guess what, more concentrated, or the absorbance, I should say, was too high to fit on the calibration curve. And then we diluted it. So we found the concentration to be 0.055. And this is important, party people. We found that concentration to be 0.055 right here. And we knew its concentration because we made it very, very carefully using the volumetric flask. What was the original concentration? Hey, there's my M. When it was just the 3 milliliters that we took from a more concentrated solution. So this is the dilution problem. And so this is MV equals MV. And I know some of you guys out there, not from my class, probably use this for titrations. I don't know why, because really you should be using moles in titration. This is the dilution problem. Molarity times volume equals molarity times volume. So that's all you're doing to solve for that more concentrated. So you notice it's 0.58 molar. Okay, and if you notice, if you go back to your graph here, okay, you can see clearly that the concentrations we have is 0.090. So we had something that went way beyond this graph, so they diluted it so it fit on the graph. That's what this is here. And then just using the formula, which is pretty ingenious, not that ingenious, but pretty smart, I should say, go find the actual concentration. So this was a dilution formula. And again, if you didn't understand I kind of explained this blurb, and I'll go back in it. Student measures an absorbance of a different solution with an unknown molarity, but of course, because that molarity is so much higher than what was used to establish that calibration curve, the absorbance was too high for the graph. The student then transfers 3 milliliters of this more concentrated solution and then dilutes it to 25 milliliters to make that solution. Okay, and then takes some of that and puts that through a spectrophotometer and reads this absorbance. Then they take that solution, or at least now we're going to now try to find the what? The original amount. Knowing that we used 3 milliliters of a more concentrated solution before we actually diluted it, let's go find the molarity of those 3 milliliters. And that's what we're doing. We're kind of backtracking here. So love the problem, really do. It's a little bit of reading here. Okay, I know you're tired at the end of the test, but that's what this question was about. I probably prefer this question more in the front end, not in the back end, but still a great little thought question to make sure you understand how spectrophotometry works and using the dilution formula and how we can still use that curve for a more concentrated solution. All right, so in any case, great little problem here. All right, so on to part C. Question 6, part C. So continuing on this trek of questions based upon spectrophotometry, here comes part C. The concentration of the vanadium solution calculated in part BII is lower than the actual concentration of the undiluted solution. So what they're saying is what we just calculated here in III is actually lower than what we're supposed to get. The student claims that the calculated concentration is too low because during the dilution step, don't forget that's the step where we took 3 milliliters of a more concentrated solution and we diluted it in 25 milliliters to fit the calibration curve. Any case is too low because of the dilution step. The final level of the solution was higher than the mark on the volumetric flask. This is important. So when we diluted that 3 milliliters into the volumetric flask to make a 25 milliliter solution, we added way too much fluid that went past that calibration line. And therefore, we actually have more than 25 milliliters. If we're going to have more volume than we anticipated for in our calculation, that's going to make our molarity more diluted and lowered. Okay, and therefore we had a solution that was more diluted. If it's more diluted, hey, we're going to measure a lower absorbance. But getting back to the question here, all right, the student claims the calculated concentration is too low because during the dilution step, the final level of the solution was higher than the mark on the volumetric flask. Do you agree or disagree? Well, if we're going to add more water than we're supposed to, our 25 milliliter solution was really 26 or 27, then our molarity is less than what we were using in our calculations. And that means that the absorbance that we measured from the calibration curve that we have in the beginning part of this question gave us a molarity that was also undervalued. And then we use that undervalued, right, here using the dilution formula to solve for this molarity. And if you use the equation to solve for M, a lowered molarity here is going to lead to a lowered molarity of the more concentrated solution. So many ways to answer this, but you should agree wholeheartedly that the calculated concentration is too low. Okay, a couple ways to say this. Here's what I said. If the student added too much water in the dilution step that was higher than the calibrated mark for 25 milliliters, then the concentration has a smaller molarity due to a larger volume. That to me is important to state of the solution. A smaller molarity would lead to a decrease in the measured absorbance because A equals EBC. And of course, a lowered absorbance is going to give you a lowered concentration or molarity that we use to calculate with. Okay, so that to me is a good complete answer there. All right, so any case, on to question 6. Question 7, part A. Here we go. It's back to some thermodynamics. So we've got an equation here. They give me the delta H of the reaction. It's exothermic with this negative. Okay, so they're giving me some standard enthalpies of formations. These are heats of formation. And so part A reads, based on the information given in this table, calculate the value of the heat of formation for sodium oxide. Classic AP problem. If you've done your work here, you should have seen this before. So if you haven't, we're here to learn. So in this question here, I gave you the equation for how heats of formations can be totaled up to get the overall delta H of the reaction. In this part of the course, most of your calculations for either attaining an enthalpy of a reaction or the overall entropy or the Gibbs free energy is products, the sum of the tabulature's value, products minus the reactants. The only exception, and I bring this up because they tend to bring this up a lot, not in this test, is bond energies. Bonds broken minus bonds formed. That's reactants minus products. But most everything's products minus reactants, and they give you this formula. So all we got to do is plug in. We know the delta H of the reaction. It's already given to us as negative 828. Don't forget your negative signs here. Direction matters in thermodynamics. So we're going to plug that in for the overall reaction. Now we have to understand it's the sum. That's what this little symbol is, the sum of all your products, heats of formation, minus the sum of all your heats of formations of your reactants. But careful, heats of formations are kilojoules per mole. So you have to look at the stoichiometric coefficients of the reaction. So take a look of the reaction here. We have 4 sodiums, 1 oxygen, making 2 sodium oxides. Now careful here, recognize the fact they were very nice. They gave you the heats of formation of the elemental states. You should know that they are already 0 from this course. So they were very nice to remind you that elemental states don't have a heat of formation because they were already formed before we could measure them. I call those the phase zone, the free atom zone, or hey, they were formed in the Big Bang or the production of the sun or whatever you want to talk about. Okay, but they were formed before we could measure them. So these guys will be 0. But remember, it's products minus reactants, and because there's 2 sodium oxides, we're going to basically make that 2x. We're trying to solve for the sodium oxide, so we needed the 2x here. That's the little wrinkle in this question that might have made it a little bit difficult. And of course, I have the zeros here, 4 times 0 plus 1 times 0. And again, that's very nice for them to give you those zeros. Any case, so now it's just, guess what? Negative 828 equals 2x. I think we can solve for that. And if you messed up on this problem, it's probably because you didn't recognize that this was 2x. You may say, wasn't the whole thing equal 2x? No. We're solving for what? The sodium oxide per 1 mole. That's what a heat of formation is. And the coefficient has a 2 there. So that means that you have 2 moles of the sodium oxide is contributing to all of this energy per mole of reaction. Okay, so in any case, 2x equals that. Of course, you divide by 2, you get negative 14. Mathematically, it's simple, like most of the things that we do in chemistry, but what the numbers mean and what the concepts are behind the math is what we're all, us teachers, trying to get you to understand, so that when they throw a little curveball at you like this 2x here, you said, oh, I see that, this is per mole. Okay, and the reason why it's per mole is because it's a state function. The energy per mole that we get out to form these compounds doesn't change under different conditions. It just matters how much we have, and per mole stays constant. So that's the answer to part A. On to part B. On to part B. Part B, we have 18.4 gram sample of the sodium reacts with 12.8 grams of O2. So you got to sniff out these questions. They're giving you information about both reactants. I rewrote the equation and I rewrote the delta H of the reaction, both of which we need for this question. But you need to understand, if they're going to give you the amount of their both reactants, and we want to know how much heat, which is a product here, how much heat is going to be released, then we've got to figure out how much this reaction goes forward. This is thermodynamics. This is not equilibrium. This is a limiting reagent problem. You need to sniff it out. They love limiting reagent problems. And how do you know? When they give you the amount of all the reactants, and you've got to figure out which reactant's going to run out first. So I have here is a stoichiometry table, not an equilibrium table. And in my stoichiometry table, I don't put grams. I need moles. I need a how many value. Why? Because the ratios here are important, right? So the ratios are important here, as I just said. And it's a 4-to-1 ratio, and that's a how many ratio. So my friends, in chemistry, we need to figure out our moles. So I gave you a little snippet of the periodic table so we can get the atomic masses, and I converted the grams to moles. Nice numbers they gave us, 0.8 and 0.4. And I'm going to put that initially here. Okay, I'm going to zoom in onto my stoich table so we can see what's going on here. So I put the moles in. I have to be in moles. I have to be in a how many value to use the how many ratio. So how do I go about this analysis to find my limiting reagent, to see who is actually dictating how this reaction or this completion reaction goes forward? So I see that, okay, if it's a 4-to-1, in order for the Na to be the limiting reagent, and all of this value to disappear, 4-to-1, I need at least a fourth of sodium's value. What's 1/4 of 0.8? Okay, well, that's going to be 0.2. So the question is, do I have enough oxygen to completely react away sodium? And I do. All I need is 0.2. This 4-to-1 means all I need is 1/4 of this value of oxygen to make it what? Completely react. That's the way that I love to teach it, because you can see the relationships here. So what's 1/4 of 0.8? 0.2. So this is going to be minus 0.2. And I know you don't need this part, but at the end of the reaction, there's going to be 0.2 excess. You might need it for other reactions, especially if it's a gas flow problem, or a gas, or I should say, especially if it has vapor pressures. Any case, if I look at this here, 0.800 is going to completely react away. That's my limiting reagent. Now, if you don't follow me, let's do the analysis the other way. How much of the sodium do we need to make all of the oxygen disappear if it was going to be the limiting reagent? Well, because it's a 1-to-4 ratio, right? 1-to-4 ratio, that would mean, party people, that I would need 4 times that. Okay, I would need 4 times 0.4, which is 1.6, and I clearly don't have enough of that there. So that would mean that I don't have enough sodium to make all the oxygen disappear, and oxygen is the excess. So we kind of determined that. All right, so again, we have more than enough oxygen to make all the sodium disappear, and now we've established sodium is the limiting reagent. So it's going to lose everything, minus 0.80. This is minus 0.2 because it's a 4-to-1. And notice the products here. Okay, I'm just going to fill it out. 4-to-2, it's half that, so minus 0.4. So at the end of this reaction, we've produced 0.40 moles of Na2O, or we've used up all the limiting reagent, or so forth and so on. This tells us at the change how much we actually reacted to reach completion. Okay, so that's the first part, and that's probably, you're going to get 1 point here somewhere to know who your limiting reagent is to start the problem, because I believe this is a 2-point question at some point. Any case, the second part states, okay, now that we have an established who's going to stop the reaction, 18.4 grams is going to be totally reacted away. That's my limiting reagent. Okay, according to the equation, they wanted us to calculate the total amount of heat released. Okay, so I could actually start this reaction or do the next part with any one of these values here. Okay, I just chose to use the sodium. Now, notice this is delta H per reaction, or better yet, it says -8 0.28 kilojoules per mole of the reaction. So what that means to me is that if I have this reaction occurring a mole of a time, 6.0 times 10 to the 23 times, you can clearly see that there's 4 moles of sodium that are going to be used up per 1 mole of this reaction occurring that many times. So that's the ratio here. There's 4 moles of sodium for the amount of energy that's reacted per a mole of the reaction. So we start off with exactly how much sodium reacted, okay, and then we use the ratio that there's 4 moles. So now I'm going to cancel to make sure everything's correct. I'm going to get rid of my sodium to get my energy. So this is stoichiometry, and then we're going to get rid of a mole. And all I'm going to do is take my 0.8 times this times 828 kilojoules, divide by 4, and I get my 166 kilojoules. Okay, so again, this problem, nice little problem, we needed to figure out the limiting reagent first, and then use and understand how complete these reactions are occurring, and use that value to answer the energy. Now, again, I could have answered this using the 0.2 moles of oxygen, and I would times that 0.2 directly, okay, to this equation here, because it's a 1 here. So I would take, guess what? It'd be a fourth as high, right? So 0.2 as opposed to 0.8 would give me the same answer. Or I could also use the sodium. There's 0.4 here. And now I put a 0.4 here, and I have to put the 2 underneath here. I'd still get the same answer. So as long as you pick exactly how much reacted or how much was produced in the change, and you have the right ratio here, you get the same answer. So nice little question of a limiting reagent problem. I use the Stoich table, then figuring out exactly how much any one of these 3 reactions are reacting, use those ratios and do a little stoichiometry to find your energy. Remember, the energy is per mole of the reaction, so you've got to consider the mole ratios if you're calculating energy here. All right, so on to part C. Question 7, part C, the final question here, and here we are with the lattice energy question. So lattice enthalpy can be defined as the energy required to separate an ionic crystal into gaseous ions, right? We're going to pull these ions away, these ionic crystals, into gaseous ions, and see how much energy it takes to do that. So we have rubidium oxide, Rb2O, and we have sodium oxide, Na2O, have similar crystal structures. Their lattice enthalpies are given in table 2. So when they say similar structures, is that, well, sodium is +1, oxygen is -2, so they make the same arrangement. So the crystal structure is not going to come into play. It's just the charges between the ions. It's the force of attraction. And they're saying in the question, using Coulomb's law. So my gosh, you better use it. Using Coulomb's law, explain why the lattice energy of rubidium oxide is smaller. So why is rubidium oxide smaller? Why does it take less energy? Well, it's because rubidium oxide has a lower force of attraction between the ions, the positives and negatives. And what is Coulomb's law, party people? Coulomb's law is the force of attraction, electrostatic attraction between positives and negatives. It's equal to a constant, that's not really important here, times the size of the positive charge times the size of the negative charge, divided by the radius squared or the distance squared, however you want to think about it. So we're dealing with -2 for both of these ions, or both of these salts, these crystals. So that's not a factor. Okay, and of course sodium and rubidium are in the same column, column 1. Okay, so they're both alkali metals. They both become +1 if you do the oxidation state. So guess what? The +1's not a factor either. The factor is the actual radius of the ion. Now why? Well, the factor is if I am a larger positive ion, which rubidium is, and I'm trying to attract a smaller -2 ion, right? Oxygen is a nonmetal, it's smaller. It does get a little bit bigger when it gains 2 electrons, but overall it's a smaller negative charge. This -2 is only going to feel a fraction of this positive charge, right? Because it's so big. Now, if I was to redraw this and have a -2 here for the sodium oxide, it's the same oxygen's -2, but now sodium is a smaller positive charge, which means, okay, that this negative charge can feel more or almost all of this charge density, whereas the bigger ion, it feels a fraction. And that's how it works. And if you don't follow any of that, use the formula, right? The formula states that if the radius is larger, and you should know the radius is going to be bigger for rubidium as it moves to it's in the fourth, or its electrons in rubidium plus occupy the fourth principal energy level, right? That's the fourth row, while sodium ions have electrons that occupy the second. And I'm saying second because it lost its valence electron, and I'm saying the same thing for rubidium. It's actually in the fifth principal energy level when it has a valence electron, but when it loses one, it's fourth. But the bottom line is, as you go down the periodic table, the atomic radius gets bigger because electrons are filling shells that are farther and farther away, right? I always say the n number, which is the quantum number that indexes size, okay, is what essentially is the overriding factor as you go down. So any case, so with a larger rubidium, this would mean this could be sodium here, and this could be rubidium. All right, so, and this would be lithium. They're all +1, but with a larger positive charge, a larger radius. Remember, the denominator is the formula, so a larger radius on the denominator, you're going to have a decreased force of attraction. Okay, some people like to think of it, hey, if it's a bigger ion, there's going to be more distance between the bigger ion than the -2. Okay, and that distance could also contribute to less of a force, which is true. If you're farther away, that's why electrons that are held farther away from the nucleus, like in rubidium or cesium, as we keep going down group 1, they're held on to less tightly. These electrons are more easily to be lost and oxidized. These are more active metals as you go down because the electrons feel the nucleus less. So any case, you needed to use Coulomb's law. You needed to eliminate the size of the charges and focus on the size of the radius. Now, I didn't say atomic structure, just Coulomb's law. So you didn't have to explain why it was larger, but I did anyway. The lattice energy of Rb2 is smaller, okay, due to having a larger ionic radius, not atomic radius, ionic radius as a charge, than Na2. Rb electrons occupy the fourth principal energy level, while the Na plus ions occupy the second level, and thus Rb positive, I should say, is a bigger cation, just a word for positive charge. The larger ionic radius results in a smaller lattice energy due to smaller Coulombic forces of attraction between the ions. These forces increase when the radius increases, right? Again, I drew that again. So in higher radius, lower force of attraction, and therefore it doesn't take as much energy to separate these ions from the crystal. Okay, I hope this video helped in a big way in your review of the test you just took, or in a review for a test you're going to take. All right, so good luck with everything. Thanks.